Hello?
Tá, a gente tem que botar o início ali. Tem muita coisinha ainda pra fazer.
Hello? Hello?
Tá, a gente tem que botar o início ali. Tem muita coisinha ainda pra fazer.
Hello? Hello?
Não tem nada lá aí.
Pino maior que o outro aqui, não, aí eu vim caixinha dos motores. Tô vendo também, né? Eu sou.
Tu não entra não. Você é.
Eita, tem mais coisa.
Nossa. Tudo mais. Não espaço não. Não. Espaço pra ver.
Não, esse aqui eu vou botar ali, relaxa, vai ter espaço.
Eu vou ver.
Aí.
Só não tem corrida.
Hello, Ivan.
Testa aí o som.
Esse aí era pra som. Eita, tá na sua conta. Tá na sua conta.
Tá. Deixa lá, vai ficar vendo. Testa aí o som.
So, hello everybody.
Isso aí era pra... Som. Eita, tá na sua conta. Tá na sua conta.
Tá. Deixa lá, vai ficar vendo. Testa aí o som.
So, hello everybody.
Som.
Testa aí o som.
So, hello everybody.
Som.
Não, it's perfect. Beleza. Testa aí o som.
So, hello everybody.
Não, vai embora. Som. Todo mundo tem que dar pausa. Ok. Hit close up. Ok, já trouxe.
We're just setting things up to start shortly. So, if you're there and can wait a little bit more.
It's the first time we do it, so some things can go wrong. Sorry for the delay.
We're just setting things up to start shortly. So, if you're there and can wait a little.
Aí, João, tá tudo certo.
Não de que assim, eu entrando no cara.
Obrigado pela música festiva.
tinha pensado esse áudio na semana, bem ligado.
Tem, pô. Vou deixar um fone aqui pra gente fazer.
Tá bom.
Tá funcionando. Aí tá. Sempre. Não, né? Aqui, tipo, vai ficar sempre igual. Aí, tipo, quando quiser, sempre muda aqui e já muda lá. Você tem aquela imagem lá de. Espera. E agora vai no YouTube.
Aqui.
Lá no. Não, já deixa o painel de controle lá.
Do que? Do YouTube?
É,
Não, só de controle.
painel de controle. Área de transmissão livre. Caraca, tem uns 21 fios. Que legal.
Sério, vai?
Sério.
Esse time tá offline? Por quê?
Não, mas esse outro aqui tá mesmo. Porque senão você não consegue agendar. Não é ideal. Isso foi 13 e 24, então não alterou ainda. 1920.
Tá certo agora.
1980.
Só que tá cortando. Eu corto a minha tela toda. A menos que eu, tipo, diminua meu...
Não, aqui você pode continuar. Não tem como alterar isso aqui.
Pode assim entrar. Perfeito.
Esse pode remover. Vamos.
A transição tá boa. A transmissão tá boa.
If you're hearing us, we're trying to figure out some problems with our YouTube stream. So YouTube says that the transmission is very good, but as we can see, just some gray images and stuttering things. So as it is our first time,
Tá tudo normal, deixa em 80 também.
Não, calma. Codificação. Cadê aquela janela que eu não acho mais aí? Não acho, né?
Essa compressão você
Ainda
720.
tá esperando. Esperando. Então vamos voltar.
Ajuste o ecrã, ajuste o ecrã.
Inception. Faz isso aí. Vou deixar isso aqui.
Então, tá arrumando direitinho. So, as you can see in our chronogram here,
Peraí.
we're going to
Espera que a gente dá o início certinho, então. A gente mostra na câmera primeiro. E aqui tem um negocinho aqui. Definir início. Vamos definir início. Aí. Então, isso vai aparecer. E ele vai ficar mais pra cá, porque...
dar um start.
Temos o início.
Vai pro cenário.
Puxa um pouquinho. Chega mais pra trás, aí abaixa isso aqui. E a gente faz a introdução e dá mais. So, hello everyone. I am Ivan Seido,
And I am João Pedro.
and today we will try to do something cool with drones and talk about them, talk about the inner parts, about electronics, and to give you an overview of how things works. And I think you may learn a thing or two today. We are streaming on YouTube and live coding simultaneously, and we will try to keep an eye in the chat. So if you have any questions, if you have suggestions, and also if the audio and the video is good / bad, we want you to talk to us. So everything, are you all hearing us and seeing everything? It's okay? If you can give us any feedback.
Yeah.
No, puxa, tá funcionando.
There you go.
Aqui tá ok. Beleza. Ó, vou começar. Vamos explicar então. So how will this live stream work? We will do a live coding, but in the third part, and in the first part, here is the chronogram. We will do an overview, which is what we are doing right now, introduction to the drone, to ourselves, and what we do, and what this project is. João will carry on with this, and then in the second part, we will talk about the theory, and in the third part, we will do the coding. Okay.
So, the drone you're building is something like, let me pick it up here. So, we have like our first prototype here. and it's like a small, we call it the mini-hex. It's a mini hexacopter with small propellers and everything that you can control with your phone. And we're doing our best to keep it DIY. So the circuit board is one layer, for example, just to so everyone can build it at its own home and do things. The frame is 3D printed, and it's what I'm going to show you right now. We developed some versions of the frame, so switching now to my SolidWorks, and here you go the first version we developed, and this version was like printed in 2 hours and in a Cursor i3, and here is what it looked like. Um, Let me change it to the is what it looked like in the first. So we had like a heavy system, and we thought like, let's maybe change some things to give it give it less weight. To let's take some weight out of it. And so this was the first prototype. We looked at it and saw like, no, it's heavy. We can do better. And so I designed it in SolidWorks, and after this first one, I thought it was heavy for the drone to fly, so I changed it to this other version here. Like we called it the version 1.1, and the arms are like narrow, and it's a lot more. It has less weight. It has less weight than the other version, and we liked it, so but we thought we can do better again, and we can improve like some points and give it less weight, even less weight. So then we switched it to the to other version, and the other version was like this. We added some holes, added a lot of things to make it even lighter, and we printed all these prototypes to just see how they were working, how we did some strength tests too, just to figure out if it was like strong enough to survive crash or something like that. We used some softwares, we used some real life testing too. That's why some of our drones are broken apart, because we throw them in the floor just to check out how the strength was. And we figured out some small problems in this version 2, and we jumped to another version that I call the version 1.3. Like in the corners of the hexagons in the board, some corners gave you less strength, so we try to give it a fillet to make it stronger, and that worked very well. And in our simulations in ANSYS, they were very good. So after all, this was the final design, and we just tweaked it a little bit to fit the drone. So in this other version, we gave it these tabs. These tabs are going to hold the board, the circuit board, so to control the drone in place. And the there's a small part here to level the board, so it can be gripping to this small parts here. Um, And after this, we realized some other things and developed the last version here. That, for example, has some squares to pass the motor wire. So we do not have to pass the wire first and then solder it. We can solder it outside and then pass it inside. So this is the last version of it. Um, it's very lightweight. It's like 9 grams or 11 grams, something like that. I'm guessing because that's what the MakerBot software says to us, and we don't have like a weight at home, but that's what we have in the mechanical part. That's the project of the micro-hex. Um, Here it's I can show you some images of it, some prints. This is the last one, the one that is with our motors and everything. We printed it in like 1 hour, and yeah, it's just this. This was the first one that I was showing you. So this was like the second one. You can like spot the difference between the arms. This one was like double the weight of this one. So then we jumped from this one to this one, and like this one you can see through, and it's like again double the weight. So we did everything we could to to have less weight, to be lighter. And yeah, it's really this. This is was one of the last prints. It's another one of the final version. It has like the squares that I talked about to pass the motor wiring and the small clamps for the PCB. Everything is in this small version, last version here. Um, as as I talked about, we have the PCB. Our PCB is only single layer, so we wanted to make our best for to be DIY, to make the project DIY. You can do to make you do the project at home. Because sometimes if you have some SMD components or if you have a double layer board, the person will look and oh no, I have to do some double-sided board and oh SMD, I don't know how to solder it. So it will hold the person up to try our project, and then we tried to do it like single layer. And I'm going now to talk to you a little bit about the board and what is like, inside our our drone. Um, Here I'm going to show you the Autumn Designer project. I plan to do it on Eagle too, just because Autumn Designer was giving me a better view of the board, because it's such a small board that I had to deal with constraints with the components like the IMU and the ESP 8266. So now I'm going to switch to the Autumn Designer, and here we go. First of all, every drone needs to have like an IMU, that is a inertial measurement unit. So in this build, we have an Chinese IMU that's called the GY88, and what the GY88 has is an MPU 6050 and some other cool things like pressure sensor, air pressure sensor, and a compass. So we can actually know about everything that the drone, like its orientation, where it's pointing at, the air pressure, so we can know the altitude and other things. So here in the project, we have our GY88, and it's plugged here to our 80 mega 328. The same in the Arduino. We are using it in 80 mega 328 to power the board. I'm going to show you here in the camera. This is the GUI88. So we have it. This is small board. and it has like the accelerometer, the gyroscope, the compass, and the barometer. That is the air pressure sensor. And here we have the board, and it has an 80 mega 328, a PT8 package, so it's deep. And yeah, it's running at 8 megahertz, so we're trying to do our best in coding to like use the power of the Z Mega at 8 megahertz. And yeah, this board was very difficult to make because it's like so small and it has a lot of components on it, but it's working very well. We have our motors, there are 6 motors, and we have like these motors, and they are DC motors, so they are continuous current motors, and they work very well for like mini drones like this. We've seen some like crazy fly and other things using the same motors, and they're working very well. So as I said, they are DC, rated for 4.2 volts, or that's the maximum charge of one cell lipo battery, and we have 6 of them. So in our board to control them, we have some small transistors, 6 of them, of course, to power the to control the power of the motors. So we can use PWM on the Arduino to control the motor power, so we can like make the drone fly. Um, so in here in the Ultimate Designer software, I have all my transistors. It's a BC337, and we give it some storage protection like this diode. And yeah, it's pretty straightforward. It's just some transistors acting like valves to turn on the motors, and we just need one direction. The drone do not need to reverse its motors, so we just need one transistor to power up the motors. We have some things here like the battery sensor too in our 18 mega, so we can like sense the voltage that's in the drone, and make it like stop or get to the floor or land when it's with low battery, and to make the communication between the phone or the computer in the drone, we use this guy here, the ESP8266, and what it does is that the ESP, it's a nice and cool microcontroller that I don't know, some Chinese company created, and it can like generate or connect to a Wi-Fi, and you can like do some cool communication with it, and it can interface with like the 80 mega and the Arduino through serial or I2C or I2C or something like that. In this build, we are communicating via serial interface through our board. So that's why I have the RX and the TX here, and yeah, that's pretty what's in the board. We have some header for the TDI to program the Arduino. The ESP, we are programming it outside of the drone because it has to plug into its own FTDI and something like that. We plan to improve this too, to make like some switch between what to want to program. Like you, now I want to program my Arduino, and then you switch and use the same FTDI header for the two. But right now it's just this, and that's pretty much what I have to talk about the board. It's an 80 mega, and the IMU we're using is a GY88 that has an MPU 6050 IMU, and it has like a gyroscope and an accelerometer. And the MBU 6050, it's very good at doing like sensing its accelerometer and its gyroscope are very good. So can switch now to the camera. Our what our board does is that it gets the data from the GY88 and like the GY8 and the MPU 6050 with some cool features that like it can process the data from the accelerometer and from the gyroscope and give us the values like all filtered and all like give us nice values like not like noisy ones, and we can work with it, and it can process some cool algorithms that will filter the readings just in the IMU, so we don't have to waste some processing power of our 80 mega that is low because we're running at 8 megahertz because of the small voltage that's coming from our battery. That's one of the things that I had to think about in doing the board, because we're going to power this thing with one cell lipo batteries or lipo batteries. So we had to thought about the power consumption and the voltage that is at maximum 4.2 volts. So to work with the 16 megahertz, the Arduino requires something like 5 volts or 4.8, and our maximum was 4.2. So we had to cut things a little bit to get to 8 megahertz and power up the Arduino with 3.3 volts. Um, yeah, for the board is just this, and we this first prototype we milled it like here in another mill, and it worked very well. It's very easy to build, very easy to assemble, and for the electronics, I think it's just that. One problem we had was that the battery we bought some like cheap Chinese batteries to try. And let me see if I can find them here. Like, yeah, I got one here. We bought these cheap Chinese batteries, but don't buy them. Just don't buy them. They are one of the worst batteries I've tried. They can't hold up like 2 motors, not even 6 motors. So we were trying to figure out and we're buying another batteries to test the drone. So that's why I have to talk to you about electronics. Um, if someone has like question, like from live coding or some other website, I can answer like about the mechanics and about the electronics. And now their website. Uh, so
Well, our project is it has a few points to be finished, and the idea is that we take this simple drone here. It doesn't have a camera; it's just a drone, so that you can learn and you can play with it. And we put it on Catarse, which is it's like Kickstarter but in Brazil. So at the end of the video, we will be putting the link if you want to be notified when we launch that. It won't be expensive, even more if you are not from Brazil. Uh, and you can help us make this happen, or you can make it on your house as well. That's not a problem. The code, the project, the mechanical part, the electronic part are not yet on GitHub, but they will be. So if you are thinking, oh, I want to do that in my house, how can I do that? Well, just wait for a few weeks and we will be publishing that on GitHub. Who is in this project? It's me, Ivan. It's João Pedro and also Vitor Paganini, who is not live streaming here, but he is part of this project as well. And you may think, oh, they are going to sell this, but they are showing how to do it. What the hell? So that's basically open source. We are open sourcing this, and we are in the move to make people like drones and not only use them, but also build them. And to be truly, I have never built a drone before, and this is the first time I have built one. And I think João Pedro has built lots of them, but I am more the software guy, and he's more the electronic guy, and Tito is also the electronic guy. So we are improving this project, and you can all help us do it better. Uh, well, I am going to switch to my computer now because I'm going to do the live coding here. And if you have any questions regarding electronics, the mechanical part, even I don't know, I am
Mentions or suggestions like, oh, you can improve something like that, or you can like make it even better at switching the IMU or switching the ESP to another
yeah.
thing. If you have like a
Feel free
suggestion, if you
to
free to leave
suggest
a
that.
comment in YouTube or livecoding.tv, something like that.
We are going to put this link so that you can subscribe to this project. It's a Google Forms we have been doing. So John is going to take the link and we can publish here. Well, so you may think, okay, so how are you going to code a firmware for a drone if you don't even have a working drone? That's a good question. Well, I made that question, so I can answer it to you. The idea here is not to make things work, but show you how things can work together in a, medium-sized application. So I have seen lots of codes from drone firmwares, and you can talk, you can say it as a framework, but some of them are pretty messy. Some of them are really organized, but they do coffee for you. So we don't want to do coffee here. We want to make a drone fly and be safe, so that if it falls, it stops, and also be controllable. So everything in its place make the drone works. Some pieces missing, we will not get the drone to work. So we will focus on the essential parts of a drone that needs to be done so that it can fly. Okay, you will not probably see a drone fly here. So if you want to see drone flying, just go to YouTube. There are many of them flying and crashing, and the crashing are most exciting most of the
So
time.
we're now going to switch to Ivan's computer so he can do the live coding. And while we wait, that just I'm going to show you like the parts we used again. So this one, and yeah, this is the normal part. Like a lot of components inside, and the back of it is like almost full. And we have the ESP8266. And the camera is not focusing, so I'm not trying to focus it again. And the IMU is something like this. We were having, like I said, some trouble with the battery, so that's why we have this large capacitor here, because we tried to keep the voltage drop that we were having out of the IMU and out of the system by putting some capacitors, some future capacitors, but the problem was really the battery. So I will like remove capacitors from here, but that's overall what we are using. The GY88. You can find it on the site, like some Chinese websites and buy it for like $10 or $8. I don't know what the price is now because they are always dropping or getting higher. but it's like this average, like $10, something like that. And that's what is going to be talking a little with you. Like the center part of the drone, it's the IMU, the part that the drone uses to sense its position. So it's one of the things that he's going to talk about here.
Okay.
The, yeah,
I
these
know
are
how it's better now.
that's it. I'm going to switch my weight screen. So
Eu só entendi os motores. Então, ou ele vai ser assim, ou ele vai ser assim. Então, eu vou assim, ele-
I think it's okay.
Não dá pro microfone do Mac, né?
Eu mudar pra lá, peraí. Isso. Tá, abre aí agora o stream.
Eu tô procurando isso aqui na.
Peraí que eu vou fazer ainda. Peraí que eu vou fazer.
So let's test the audio again. Can you hear me? That would take 20 seconds to get a response. So
Tá, eu deixei aqui agora. Vou ficar essa bateria agora no fundo.
So let's test the audio. Please tell me if it's working, because I don't have feedback here.
20 e poucos. Mas tem que. Não sou noturno. Tá muito alto a negócio. Aí, solta aí, solta aí. Fura esse daqui também, esse aqui também precisa ser furado. Todos que foram furados precisam ser furados. Porque não tá passando.
Não é ele aqui? Você não tá com melhor, não?
algumas coisas não vão entrar. Partidas, eu gosto daquele filme, não vai entrar. Mas, se já vai lá, deixa.
Agora vai. Vou botar a câmera mostrando aqui, que aí precisa dar uma dica. Oi? Aí só dá uma. Ver. Cara, esse som tá fudendo. Esse som tá fudendo.
Patinão, assim, subir. E as mãos assim, frio.
Meu PC vai explodir. Bom, hello everyone again. I think everything is fine now. This is the first time we do a live streaming, so please give any suggestions and any feedback about problems so that we don't speak to the walls here and you are not hearing us well. This is a sound test, so please just say, okay, it's okay, I can hear you, I can see you, so we can continue with everything. Okay, so audio is okay, online coding, so we can continue. So here's our schedule, okay? The overview is what João spoke to you right before me. He showed you the electronics and so on. What we are going to do now is to go on each part of the theory so that we are all together on this. I don't want to start coding stuff that you don't understand. So I will explaining on the go of the video, but it's a good idea to show you about a few things before we start. I started coding for robust applications in Arduino about 2 years, 3 years, and something that I really like is to have good patterns. So having patterns for me is everything, because when you start a project, you know, you may not know how you're going to do, but you know at least the global overview of it. So coding robust applications, mostly for robots, it's something that I really enjoy doing, and I have gained some practice, and I have learned a bit of a thing or two, and this has been really good for me because when I start something, I can write the sketch or the mock-up of the program and then implementing each module, and everything just works in the end. And the way I do this is with a library that I made 2 years ago, which is called Arduino Thread. It's not a real thread, so if you're saying, oh, you have implemented threads on Arduino, no, that's not true. It's just a really simple library that helps you manage multiple tasks. And when you're dealing with multiple tasks, if you try to understand them fully, like this one has to happen before this, and if this happened, you start that, and that happened, and triggers another one, and you start coding shit because your code starts to grow really fast and you get out of control of what you're doing. So I use this library to help me organize my programs and to help me maintain them, and so that other people can also code with me or after me or help on a project. So the link to Arduino threads I will post on the chat now. If you want to take a look, we have it on GitHub. And we will be using it as the core for our drone. My computer is very slow. And I cannot even, okay. Okay then. I have delay on my computer, so that's bad. Okay, the link is there. Let me try to fix this delay. Okay, I think the delay is fixed with this camera. I will try to use only this one here. Well, to begin with, I have read lots of frameworks and frameworks that are really used today, and I took some time and read everything they had to show me, and that's really good. That's always a good starting point because you are reading what people have solved, what people have made, put time on it, and solved a problem. And that's always a good start point for any project. If something is already done, just read what is done. And so to begin with, we will read or take a look into what is already made to us. So a look into drone frameworks, that's where we are right now. Yeah, this camera is much better. I don't know why I have delay on the other one. Okay then, so I have here 3 frameworks. One it's missing here. Let me download it. Yeah, I have downloaded it. Okay, helicopter. Where is it? Oh, then this is not this. So we can download it. The first one is multi-we. It's a framework for drone, which is really used. But the thing is, it's a mess. You cannot understand it because it's not well documented, and it's filled with, turn off what, or and it's a pretty mess. The documentation is lacking, but it works. People use it, and they use it without knowing how it works, probably, unless you are a developer. I'm not saying this is not a good coding. I'm just saying it's hard to people who don't understand frameworks to understand. But I read it, even knowing that. And the other one is Crazy Fly, which is not a framework, but it's a firmware for a real drone. So Crazy Fly, it's a micro quadricopter, and the framework is written in C++, but it's running on an ARM. So they have a more robust interface, and pretty much anything that operating system gives you. The code is well organized, and that's a really good framework. We'll go into both of them, and also Arduino Pilot, which is the one I'm going to download now because I didn't have time before the live stream started, because I don't know why it vanished from my computer. So copter. Okay, let's see my desktop now. So I'm going to download the Quaternion firmware. It's not as easy as you think. Introduction. Add the pilot timer. Optional mission time. I don't know where I downloaded it, but I managed to download that. Developer tools, maybe. APM. Then GitHub. Okay, let's download it on GitHub. That's it. The Japanese guy is doing Japanese things right now. It's working. He will be back. Okay, so we have our deposit here. Let's include it into the Sublime text. Okay, so we have the three of them. And the last one is EasyFly, which is the name I gave to my mock-up of this video. Okay, so it's a working prototype for the firmware. We are going to redo it in this class. Multi-V, so just to show you, this is the parent for almost every file they have. It's a mess, but it works. It works well. Okay. They are separated into files, so you can see alarms, EEPROM, GPS, IMU, which is inertial measurement unit, LCD, multi-V, which is probably the root of the code. I will just topicalize everything. I don't know if that word exists. Output, probably to output to the motors. Okay, I have read this already. Protocol, which is the protocol used, maybe, let's see, yeah, the protocol used to communicate, change settings, and also to receive commands. RX, probably where the command from the receiver arrives. Sensors, everything sensor related, maybe, let's see if they have barometer, yeah, barometer, and a lot of things. Serial and types. Usually types is something included in all files. Okay, we'll go into it just in a few minutes. So this is multi-V. It's a mess, but it works. Crazyfly, it's also a framework, a firmware for a drone. And in modules, you can see it. It's also organized. And the code, let's go to the implementation, not the header. The code is much more readable and separated. I can read it. I think you can read it too. Okay, not in this speed, but you know, just giving an overview. And the last one is Ardocopter, which is a bunch of files, but they are really well organized. Just to see, we have here a header, which it doesn't do anything, but you know, there is more documentation than implementation. Okay, this is, let's go to the root program, which may be, where are you? Hey, Ardocopter, here. So just to begin with, they have many people working on this, which is awesome. And they use probably really much like we are going to do with Arduino threads, but maybe in a more fashion way, or even more reliable, not reliable, but more efficient way. So they define tasks for everything. They define the period for each task, and they define also the time taken to complete that task. We'll go into it more deeply. As you can see, the setup, the whole code, the main code, it's readable. They have like methods for each part of the code. It's not like we have a big code full of things inside that you cannot divide and modularize. they are well modularized, and you can understand that because of this. And in the main loop, which is something really cool that we are going to do, where is it? I cannot see it here. Setup, read, and loop. Let's see, loop. Maybe it's not here. I want to find it. Copy. Okay. So okay, this is what I wanted to find. This is the loop of the whole program. As you can see, it has just a few lines of code, and basically it waits for a sample, it gets the time, and it then computes the available time, which is the time taking for the loop to run less the time expected to you to loop that. No, no. And here we execute things that are fast, and here we do what is scheduled. Okay then, so that's 3 frameworks. Now I'll go into the crazy fly and let's understand each part of it. Okay, so right now we are in the second, yeah, in the second part of the second part, okay, which is modularization, grouping things together. So let's go there. Well, to begin with, let's start in the main file, okay, which probably is the system. I know it's a system because I read it, but I will use probably because that's how I think when I start reading a code. And as you can see, they include lots of stuff. Let's go into the important part, system launch. Since we are using ARM 7 here in this crazy fly, they have actually running threads and threads implemented on the hardware. So that's basically a method that you can say, oh, okay, I want to run system tasks, and the name of that thread is this one, which is probably undefined here. And this is the stack size. You need the stack size so that you can or, separate memory for each task in the processor. Stack size is like when you run a function, that function is stored in the state of the processor, and you can then run that function, and if it calls another function and if it does more things, they will go growing and increasing size of the stack. And when you switch to another thread, which is another task, that stack is saved and the other one is recovered and it continues. So if you overflow that stack size, you fuck your processor, not your processor, but your program, and things stop to work usually. The priority, so if I have two threads that need to run, which one is more important? Okay, so this is something that the whole system does. This is a library, okay, and here is the initialization. As you can see, we have initialization that do stuffs here. I will go through each one of them. System test, which is basically to do tests if it's working, okay, but we won't cover that. And this is the system task. So the system task is basically the root program, and where okay, here. So in the system task, it is initialized everything. So it's basically the setup of the Arduino. Okay, that's how they organized this program. And LED init is basically a function that you can some method. Let's find that method here. Let init. Where is LED init? Probably not in modules, but in how, which is hardware. Let's see if we can find it here. Okay, not here. Finding the whole folder. Okay, so here is it. It is inside drivers, so that makes sense. It's a driver for the LED. And LED init basically set up the GPIOs. So let's see that as it is. LED set basically changes the, I don't CH LED to 1. I won't go step by step because that will take time. The idea here is that you can understand what it's doing in the overview on the overall. Wart init, wart is the same as serial, so in Arduino we would do like serial.begin. Okay, and system init, that's basically the initialization of the self-system, should be in the same file since we are dealing with system. Okay, it is in the same file. So this, just for curiosity, is basically is it initialized, and is_init is a variable which is stored probably on the header, not here. Where is it? Oh no, it's in the implementation. So it's a boolean, it starts with false, and if it's already initialized, you don't do that because you don't want to do things twice. This starts the threads, probably pm init, do something that I don't think it's important for this video, but let's make sure. Pm init. Okay, pm init. Power management. Okay, that's important. Power management is usually where you store methods and the actions that read the battery value, reads if the whole management of power is okay. So in this case, if the battery is running low, you want to warn the user, and if the battery is really low, you just want to shut down everything and stop flying, because that will damage the battery and also may get out of control your drone or robot or anything. So this is where that part is initialized, and that makes sense because it's inside the system. Okay, the system takes care of that in a large overview. And then com init probably initialize the communication. I know it's the communication, but let's just go to that. Probably it's in driver, but it's easier to search. It is located in source. Com init basically initialize the USB, the radio, and all this radio and communication related things. And then we print some stuff. Okay, and then commander, which is an important part for a drone. Commander, it's basically the guy inside the program that is commanding your drone. So I want to go forward, I want to go backward, I want to go left, I want to fly, I want to stop, I want to do whatever you want, auto explode and drop bomb, and those things are the video is off. Not for me. The video is okay here. Yeah. Is it okay? Okay, let's continue. So in Commander, basically it reads the radio or whatever you are using to control your drone, and you set that command to the drone so that it can act upon your intentions. Continue. The stabilizer is also an important part of the drone. So you can think as commander, the one who demands something of the drone, and the stabilizer are as the slaves who does what the commander wants to, and also make sure the drone don't fall. So stabilizer is the part where you put all your control, which in this case is PID, and here is the command, the stabilizer. Roll rate desired, pitch rate desired, yaw rate desired. We'll go through this in a few minutes. And also initialize the IMU, initialize the motors, the fusion of the sensor, and also the controller. The controller is another important part. The controller is where all math is stored. So you can think in the drone as the heart of the drone as basically the commander who demands things front, backward, and also the controller who makes sure to not make the drone explode / fall, and also the sorry, I mess up things. It's not the controller, it's the where is it? Stabilizer. And the controller is the one who do the boring part of math. Okay, and the stabilizer also does what the commander wants to. So information is going through in this way, okay? If we think about the topology, I cannot make a vertical bar. Damn it. Okay, I've done it. So beautiful. I cannot align it. Damn it. Okay, it will be like this. And that's how it is done. The commander is the one who demands things, but who demands things from the commander is usually some program that is listening on the serial or something like that and translating that command to the commander. So we have like the radio, we have the radio again, or anything radio related. In this case, NRF 24L01, or maybe the SSP8266, or maybe a Zigbee. So we have that layer, and it is usually called, I'm forgetting the name of things, the controller. It's inside the controller. Sorry, not inside the controller. Where is it? The system. Oh, sorry, the commander. So the commander demands and listens to this thing. Also, we have the controller, and deep down in the hardware level, we have the motor part, where the motors are really set and updated in hardware. So these two parts here, they are not hardware related. And this part here and this part here is hardware related. So in hardware related, we will have also the motors. And in motors, it's really cool to make sure that your program is not working with the hardware. So let's say, to make it clear, if in the controller the PID outputs something like from minus 255 and 255, that's not intelligent because, well, if you change your hardware and then, I don't know, the PWM is not 8 bits, it's 10, then you'd have to change the controller. But if you make sure that is between minus 100 and 100, or maybe minus 1.0 and 1.0, this is not so good in our case because we will be using floating points and that may slow things a little bit. So let's make minus 100 and 100. When you send it to the controllers, you send it 100 and it will convert to, I don't know, 255. And if you send it minus 100, it will change the input pins and invert the H-bridge port, okay? But in the case of a drone, you don't want to go down, so it's basically 0 to 100, and this is 0 to 255. Also, in the hardware part, we have the IMU, which is the software where it gets information from the inertia, okay. And we also have the attitude. And you may think, oh, is it the attitude of the drone? Is it something attitude related? Well, I am Portuguese and from Brazil, and when I saw that the first time, let me see it here. Where is it? Attitude. I thought that it was a written mistake, a spelling mistake. Here, for example, attitude, controller, attitude. And when I saw it the second time in Copter, I thought maybe I'm crazy and I don't know what attitude is, but let's continue. And when I saw it in the third framework, I was completely sure that this was a new thing to me, okay? And then I looked into Google, and it basically showed me attitude things, but when I searched for attitude drone, I saw that, well, that's basically another concept in drone. So that's where I started digging something, and Wikipedia helped me a lot because there is attitude control. And I read this page and I got what it was. Okay, so basically attitude is where, let's read it. I like Wikipedia. Attitude control is controlling the orientation of an object with respect with an additional frame of reference or another entity. Celestial space, certain fields, nearby objects. So basically, it's the part where we estimate the orientation, position, and whatever else we need, and we basically convert this sensor data into real data. In case of airplanes, they use gyroscopes, they use horizon sensor, and they use many other things. There are sun sensors, earth sensors, star trackers for, I don't know, maybe the Mars rover. When it was getting to Mars, it was using a star tracker, also known as I don't know, Otacílio. Autopilot? Not autopilot. Attitude is, it's basically the part where it makes sure the whatever you are controlling stays in place with Okay, so the question of Otacílio is like the altitude mode in drones. Well, the difference is attitude is not equal to altitude. Okay, that's what I'm talking about. When I read attitude, I was thinking that it was altitude written wrongly because it's just one character changed, but they are completely different. Altitude, it's basically basically how far from the ground is, or how far from some relative value. I make it at 16. Okay. And attitude is the orientation and controlling that orientation in a drone. Okay. So let's find the attitude here. Attitude, get estimated attitude. So here is multi-weave firmware, so that we can understand the attitude part. The estimated attitude, so it's basically getting the orientation of the drone with respect with the gravity. Okay, so it measures the acceleration, it measures anything that is orientation related. And here, as you can see, it's a mess, but okay, it completes. So in the end, we have our orientation of our drone. So it's in attitude that it takes the IMU reading. So let's go back to our, okay, attitude. It takes the reading from IMU and make it useful. Yeah, we will explain that, Salvio. Thank you. And the yaw, the pitch, and roll. There are many forms. Okay, thank you, John. There are many ways to define your orientation or the attitude. There is Quaternion, there is Euler angle, there is also yaw, pitch, and roll, which is basically Euler angles in a different organized way, but it's pretty much the same thing. You can convert from one to other, and many other kinds of ways to define and define the state of orientation. So I'll change my cam now, and I'll try to do some sketch so that I can explain you what this is. So let's create another here with view capture. Not this one. So, okay, this is the camera I'm going to use. I try to make some drawings here and explain you better, because that's how I understand it. So let's take inception there. This is my mask. Let's take this simple part here and try to understand it as a drone. Okay, so let's change it for a drone, not a broken drone, the real drone. So if we draw an X here, in this direction, that's our z. Okay, so when my drone goes up, it is increasing my z, which is the altitude, not attitude. Okay, so this is altitude, and this is attitude. Okay, the orientation. So imagine that my drone here has a front. I will make it this motor here. Tem uma caneta aí? Permanente? Show. So this is our front. I will paint it. And when you align an X with that orientation, and you have another X of the Z, the last one is the third X. Okay, so we have 3X here. When you go and with the vector that crosses the front of our drone, and you rotate along that axis, like doing this, okay, I'm doing this. When you do that, you are rolling. So that's the roll of the yaw, pitch, and roll, or Euler. So if we're steady and horizontal, that's 0 angle in roll. If you are 90 degrees left, you can say you are minus 90 degrees in roll, okay? So if you go to the right side, you are 90 degrees positively in roll, okay? Now let's imagine the other X. Let me draw it here. It's this one. When you rotate along that axis, you are pitching, okay? So the pitch, imagining an airplane, is when the airplane goes up and down. So the airplane is pitching. The pitch is changing. And here is 0, here is 90, here is minus 90 degrees. And you can actually go upside down at minus 180. And if you go a little bit more, what happens? It's not minus 200. It is actually plus 160. So that's basically limited to minus 180 and plus 180, exclusive in one or the other. Okay, so that's the roll and the pitch. And we have the yaw. So the yaw is when the drone rotates in the ZX. So you can imagine that the front is here, and we start marking this point as 0. The yaw is when the drone rotates in this X. So here is 0, here is 90, here is minus 90 degrees, and that's how it works. What is the problem with yaw, pitch, and roll? There is a name for this problem, and it's well known. Let me search on Google for a moment and get an image for that. So it's named gimbal lock. If you want to read it on the YouTube, okay. And let me show you what gimbal lock is. Imagine that when I say roll, it's this. When I say pitch, is this, and yaw is this. Okay. So let's imagine that you cannot only rotate in one X. My drone can be also like this, which is rotated in the roll and in the yaw, in the pitch. Okay, so imagine I rotate first in the roll, okay, and then I rotate in this X here, okay, not in this X anymore because my frame is rotated. So I rotate here, okay. So when I do that, the problem is that if you go, for example, 90 degrees up and then you go 90 degrees right, then you have a gimbal lock in the yaw axis, and that's a problem because you cannot anymore move here without changing the respect of yaw or the pitch and the roll. So it's a math problem, okay? It's how you define this that makes this problem happen. So let me show you a quick video on YouTube so that you can understand that lock better, okay? So my computer is fucking slow because I am streaming in HD, I think, and this is really bad. But let's try to continue. Gimbal lock.
In this now gimbal lock is
Okay, there. This video has 6 fucking minutes. This is not a good video. Sorry for the delay. I am trying to go fast here, but my computer is not wanting me to go fast. And I want a good gimbal lock explanation because gimbal lock locked my mind when I was learning yaw, pitch and roll. I had problems that I didn't know what it was. Okay then, so this is gimbal lock. This video has 8 minutes. Okay. So this is the frame where we were talking about. The yaw is in this case the rotation in the green. The pitch is the rotation in the red, and the pitch is the rotation in the blue, and the roll is the rotation in the red circle. Okay. So when you rotate, they kind of move together. Okay. And when you align one rotation with the other, you stop being able to rotate in another orientation. So let's see it here.
We can see how the rotations are passed on. By spinning each of the machine's 3 arms, we can rotate the jet into any angle. But notice when the jet points up, how 2 of the circular arms match up. This is exactly the same effect of gimbal lock, causing 2 circular arms to rotate on the same plane. Let's make this ourselves in a hierarchical system. To demonstrate, we'll grab some torus objects. They can represent each axis. Green will represent Y, X will be red, and Z blue. So altogether we have 3 toruses and an arrow object. Let's parent them together. X to Y, Z to X, and the arrow.
Okay, gimbal lock is shown here.
This is going to mimic a rotation order of Y, then X, then Z. The Y, or green torus, is the top of our hierarchy. So in this parent structure, everything rotates with it.
So this is rotating the yaw.
Affects the arrow.
Come on, video.
Because it's at
Let
the
me
bottom of
speed
the
up
hierarchy,
things.
so the last axis in the rotation
Okay.
order. X is
Almost
second
there.
in the rotation order.
So when you rotate in the row and this is in the pitch.
It's at the top of the hierarchy. Now here's where things start to get interesting. If we continue to rotate X in the middle of the hierarchy, it'll cause Y and Z to align.
And this is that lock. When you align one X with the other, and you cannot go anymore in that direction, the backward direction, or some directions you cannot go. So that's just to explain you that yaw, pitch and roll are not perfect, and that's why the IMU and usually math don't use it to compute the attitude orientation, because if you start with problematic definition of your state, then you can have many problems. And well, if that is problematic, then how can we solve that? Okay, so how can we make sure that this never happens in our drone, even if we are doing like 3D movements, which is not something covered here. But if you are in a different orientation than the normal one, which is pretty much aligned with the horizon, well, that's why Quaternion exists. And Quaternion is something really cool because it defines the same thing as yaw, pitch and roll, but instead of having yaw, pitch and roll, which are 3 different values, it uses a quaternion, which is the x, the y, the z, my z is inverted, and the q. Okay, so Quaternion, when I started reading about it, it was kind of complicated because when you read on Wikipedia and so on, they seem to overcomplicate things and you just want to understand it. You don't need to make fucking math with it. So basically what a Quaternion is a new way of showing you the direction. So imagine that this is the x, this is the y-x, this is the x, and the z is here, so it's up in the paper, okay? But I will draw it like this. So when you define, okay, my drone is in this direction here, in the x and y, my drone is pointing in this direction here. So imagine this is x, this is y, and this is z, okay? So my drone is basically in this orientation here. He's pointing the y direction, okay? Well, when you change your drone orientation, you can think that, I rotate the drone here, that the x-axis is summed with a z-axis. So we have a vector on that direction. So a quaternion, those 3 values here, are basically a 3D vector of the direction of the orientation, okay? So let's think a bit more. If I have 3 values that define my orientation, if I define the 3 values as my vector of orientation, then I will have a problem. Because imagine, I'm pointing in this direction here, okay? If I'm pointing in this direction, then how do I make this? Because the vector is the same, okay? So I cannot make with the same vector something like this or this. They are all defined as 3, as the direction of my drone. And that's why the Q exists. The Q is how much angled you are in that axis. So if you increase Q to the infinity, the drone will rotate infinitely here, okay? And if you go negatively, the drone will go in the other direction. So that's how Quaternion works. And the good thing about it is that when you are animating or doing something with Quaternion, it is much easier to interpolate. So let's say I want to go from here to here. In Quaternion, it's just a matter of multiplying and doing some the 3 rule. I don't know how it says in English. It's like when you do a proportion from one value to another and you interpolate linearly, okay? So that's Quaternion. Does this propeller cuts flash? Well, John, did you ever cut yourself with this propeller?
No, never. But I can try.
We can try in the end if you want. John is the guy. Show your hands, John.
Here are my hands.
Everything dangerous, it's he that does it. So basically, if you have any dangerous questions, you can ask him. Okay, his name is John.
So yeah, this motor is just like 4.2 volts. Yeah, they really turn at 40,000 RPM. They might not full load, but I don't think they can cut someone or maybe just paper or yeah. We can use some knives like the AK-47 knife or put it in there and try to kill people, but that's not what we want here. And yeah, the Raven Bomber says it's not useful, but we really like to fly it, and it's cool to fly drones. So we like it, and yeah, it's that. You cannot use it to kill people. We made it as a toy, so yeah, it's for you just to play and be awesome.
We have a paper written. It's forbidden to fly drones in our room, so you can expect that we have made damage to ourselves someday. Okay. So that's it. Continue on. Yeah. Show the.
Yeah, this is like in Portuguese, drone flight is forbidden because yeah, and we have like hashtag safe drone here. And yeah, like same with drones. Because someone hurt himself here in the room with a beer drone, and we don't want another people to get hurt again.
So that's it. It's safe enough. You won't kill yourself with it or anything or anyone else.
Hello, Salis.
Continuing. Okay, so Quaternion. Let's talk about PID now and the control itself.
Já tô pode tirar os buildings?
So basically, this is my screen here. No, desktop. Okay, not terminal. I want Sublime Text. Yeah. So the attitude will give us the readings in the way we want, and you may be thinking, okay, Quaternion is better to define our state of the drone, the orientation and attitude, but it's not good enough for simplified math in the drone, because when I started to look and understand about how a drone works and how the control is made on it so that it can stabilize itself, what happened was that... Are you kidding me? Que bosta, vocês estão flodando o negócio aqui.
Yeah, my friends, please stop flooding the chat. Please, Otacilio, stop flooding the chat. And I know it's you, Victor, the Arabian bomber.
Okay.
We know where you live. We're coming for you, Arabian bomber.
Okay. So the attitude that we are going to use comes from the IMU in a Quaternion state, and we convert that into yaw, pitch, and roll. And the reason why we do that is because PID, which is the algorithm using to stabilize the drone, uses each of those components. So you have the yaw. Okay, so imagine that your drone can only rotate in this axis, in the roll axis. Imagine that you have only two motors, one side and in the other side. When you rotate in that axis is the yaw, the roll. So if you put a PID in the force of the motors, you will be able to stabilize in that orientation. And if you go to the other axis, the pitch, okay, so I have the pitch here. when you pitch, is locked, so you can only pitch in that direction, and you put a PID in that value of the pitch, it will try to stabilize in that orientation. And if you release the drone and put both PIDs working together at the same time, the drone will try to stabilize in both axes at the same time. But there is also the third axis, which is the yaw, which is this. So if you stabilize a drone with two PIDs in the row and in the pitch, it will probably start to rotate along its axis. So basically, that's why we have three PIDs running in the drone so that we can stabilize it and stay still. We cannot use the attitude got from the IMU to stabilize the z-axis in position, and that's because the IMU reads acceleration, and to get position displacement, how much the drone has fall or has going up, we have to integrate that twice, and when we integrate that twice, we gain a lot of errors. So it's not safe to integrate that twice and get a reliable value of the altitude, okay, the distance from the ground. But we can kind of know pretty sure with some limitations if the drone is falling or going up, but in a really rust manner. So people don't usually use this to stabilize. Okay then, and how do you stabilize the altitude? Okay, the distance from the ground. I have seen two main uses. The first one is a ultrasonic sensor here, or an infrared sensor, a distance sensor pointing to the floor, and it's stabilized with a PID in that direction. So basically, it reads that distance and put a PID in that distance and tries to maintain that distance. Okay, and the other way is with a barometer. Barometer measures pressure, the air pressure, and if you go up and up and up and up in the atmosphere, there will be less oxygen to support, and there will be less pressure. So you can kind of infer the altitude based on the pressure you are receiving in the barometer. But it's not fixed. It's not something reliable 100%. And it varies with wind and many other things. So when there is, I don't know, a wind coming, maybe the pressure will go up a bit and your drone thinks it's going up and will try to go down because of the wind, and that can fuck you. So when you use barometer, you need to do a really good I don't know, maybe a moving average to read that. Also, how to control the drone so that those controlling values act upon our drone. Well, that's the last part. I will talk about theory here. Okay. When you want to go forward or backward, imagine that this properly here is rotating more than this one. Okay. So basically, it pushes the drone upward. Okay. And when you rotate in that axis, which is the pitch axis, you start making a force so that the drone goes in that direction. Okay, so the drone is going, and if you want to go in that direction, also it means in the going positively in the pitch. Okay, going there, you need to increase force here and decrease force here. But then you may think, okay, but what if I have an hexacopter? Okay, what if I have an hectacopter copter or anything else? We may generalize this with math. Okay, so imagine that you have 1, 2, 3, 4 propellers. Okay, and you want to go in that direction, okay, you need to increase power in this and decrease power in this. And the reason why we don't mess up with this is because it is aligned with our axis, okay? So it is aligned with our axis. If I increase power in this or decrease, the only thing it will cause is to the drone to go up or down, not front or backward, okay? Front and backward, up and down. So if I add more propeller here, let's imagine this drone here, okay? And I want to go in that direction, okay? So we can cut the drone here. And you may think, okay, this propeller here will increase power so that the drone lifts its back. But what about this one? I mean, it can also help this propeller go front. It is not aligned with this axis, and it is actually kind of this in this axis and is in this axis. So we may think about this as basically math, okay? So if we take the distance, for example, from the axis, you may generalize that to the proportion needed to go in that direction. But you can do even better if you, I don't know, take the sine of the angle. That will work as well better. But anything that is proportional in some way to the distance to the x, I think it will work perfectly. So that's how you compute the power for the pitch correction value in the drone. And the same is done with other axes. So if you want to go that direction, I don't know, 2, 3 angle and 3 degrees, you will just compute for each motor what's the distance from the x, or maybe the angle or anything else, and that will give you how much it needs to be set in the motor so that it actually performs that movement. So, well, this is the theory behind the drone flying, and now we will begin the part 3 of this course. Let me create a mark point here. So we are beginning part 3 now, and in this part we will start coding, and that's the part that most of you are interested in, maybe. And all that we have talked about here will be placed in practice, okay? Let me switch to my camera. Okay, I have it here. And let's begin with creating a new project. Let's go there. I will place it on the documents, new folder, and I will call it Easy Fly Live. Okay, so that's the name of our framework, live because I am live. Oh, that makes sense. So let's create that folder in Sublime Text. So we don't have anything there yet. Let's create easy fly live dot and this is where we will do everything. Okay, so let's begin with putting the void setup and the void look. Those are the two main parts of any Arduino project. And Let me just see one thing here. Okay. And it is in this that we will include all our libraries. So I used to include like MISC stuffs. For example, if we have any definition for types. Okay. And a configuration file. Let's create that configuration. We place it inside a .h because it's the header file, and that's a really good thing so that you can follow. Everything in the .h is not implementation, so you don't put anything that is implementation inside a h file. You only place definitions. So definitions or even the declaration of methods and the classes. So let's say if you implement something, you will not put it on the H, you put it on this .cpp. We will do it a lot here so you can get used to. So here we'll basically define a few things, okay? And this template here is what we'll always do with any included file. And don't forget the endif here. What it basically does is check if it's not defined, okay? If not defined, this define here, then define this define here, okay? Basically, it's a dumb thing, but you see how it works. When we include that file in any other file, okay? If you include it twice, for example, when it's included twice, when it goes inside it, it will already be defined. So you won't declare everything again, and you won't have any errors. Okay. So when you do this, it's just to make sure that your header file is defined only once. Okay. So let's define a few things for the project. I use this scheme for commentaries. Okay. I just put project name for now. Something that I like to do is to define the speed here. I like to use 57,600, and also define a method called log, which is really useful because it's basically forwarding the serial.print to wherever it is. So if you are using anything that is not Arduino, you can change the method here, okay? So when you use, let's say, for example, log, hey there, before compiling, the C++ is switching this to serial.print, okay? So it's basically the same thing, but it in a smaller form of writing it, okay? So let's go there in our EasyFly and begin things. Here I need to initialize hardware, right? And the hardware initialization, yeah, the header guard. The guy there said the name of it. I use it because it works, but he said the name. Let's put it here so that you can understand it. And the header guard is this choose line here and the last one. If you forget to put the endif, there will be a lot of trouble because it's like the endif will be compiled with the last endif, whatever. It will be a mess. So don't never forget to put endif in the header. Okay. Thank you, Fumanchu. Any comments on YouTube? No. Okay. So usually you start with, I don't know, serial.begin and the value here. In this case, we have it configured, so serial speed. Okay. It's a good thing to put while not serial and comma here. And oh yeah, I program one. Yeah, I don't know that way. If you can show me an example, we can test it out here. And I usually use that way because you can do it in C as well and old compilers. But there are always preprocessor directives that help us doing that. But in this way, it will work. Okay. The drone we are working on is a self-made drone. It's a micro-hexa-drone. It uses DC motors. Okay, so answering CEO Yago question. Yeah, it's Skynet first drone because it's not autonomous yet. But when it is, it will kill the whole human race. So let's not make it so intelligent. Why not serial is basically, well, wait serial to be completely configured. Okay, so if you are using, for example, Arduino DUI takes some time to configure the serial. Okay, so you do that, and it will make sure the serial is not initialized when you use serial.begin. So basically this initialize the serial, okay? And then we can print the log up. Let's print some cool thing here. And I can put log because I defined it. So up, and I will put space. And let's go and print the project name. Okay, and then /n. I like to put at least 2 so that we can separate the file when we read it on the serial. Okay, so this is our normal setup, and that's basically something you don't want people to read when they are trying to understand your fucking software. This is something that should be encapsulated, okay? And where should we encapsulate hardware related things and, you know, all that? Well, we should use that inside the system, okay? So we should only have system.init, or maybe system init, or maybe system init, or system init, or whatever else you want. So we want this here to be inside system init. And we can accomplish that in many ways. I will show you at least 3 of them, but 2 of them we will use it here. Okay, so once you answered, you can use pragma once. Okay, so let's go to the header and put pragma once here. This is the same. He's saying I cannot confirm that until I compile. I trust you, Fumanchu, but I like to test things. So let's see if it works. The reason why I'm using Sublime Text is because it's much easier, so you can read it, and also I love Sublime Text. So yeah, I like Sublime Text, and we are using Sublime Text because it's easier to write, it's easier to read, and to do many cool stuff. But I use the compiler, the Arduino compiler, because unfortunately, the new version of Arduino does not work with Steno, which is the uh, the library, the plugin for Sublime Text to compile and download to the Arduino. So let's go there and open our sketch. Where is my sketching documents? EasyFly Live. Okay, EasyFly Arduino. Let's see. Yes, I'm using GCC. Let's check it out. Okay, it's taking time, so I think it's working. This is taking too much time to compile. Maybe it's the first time. Oh, I'm compiling for Edson. What the fuck am I doing? We will be using Arduino Nano. And wait. Okay. Something.
8 MHz, 8 MHz.
Yeah. But we are using the 8 megahertz version, so that's even less. So we have it here.
Like you updated the software, so it won't be there. Use
Oh,
the
damn it.
normal Arduino Nano. Yeah. Any of them would compile to the Arduino Nano or the Arduino Uno.
Então precisaria ter isso funcionando. Tudo bem, então. Você põe ele pra funcionar. Liga tudo nele, no shieldzinho. E, puxa. 1.6.5. Okay, so we updated the software, and the problem is that this Arduino Nano that we use in the hardware is a 8 megahertz version. Yeah, we are going to make it work with the drone, but I need to update my software so that we can make it to compile it. Okay. But okay, it works. Thank you, Fomoncho. You can use Pragma once. That's a really good thing. Another tip is that when you go to the configurations of your software, you can click on Use External Editor, and anything here now is not clickable. You cannot edit it. You can only compile and upload. So that's good for this kind of setup where you have when you have external editor that is modifying the code for the Arduino. So yeah, it works. It's much faster now. That's okay. I'll take a little bit of time now so that I can put the Arduino 8 Nano 8 megahertz to work, and that's good if you want to learn as well, because if you are going to code for a drone that use one cell lipo, you need to use 8 megahertz if you don't want to boost the voltage up to 5 volts, so that you can use 16 megahertz Arduino Nano. So if I'm not mistaken, it is inside here. Where is that thing? Okay, let's go to the tutorial. So I'm going to download the Arduino breadboard configuration file. And this is the file I need. This is the definition for the Arduino software that we are using 8 megahertz. Okay, so it's basically the same thing, but it uses another hexadecimal. It changes the bootloader a bit, and we need that to download to the Mega. And the way we install that inside the Arduino is, where is my Arduino? My Arduino isn't it here? My computer is really slow. So let's go there. We need to change a subfolder in our Okay, so we need to go to our sketchbook. My sketchbook is in here. And let's restart Arduino software. Okay, it's open. And it should appear here now. Okay, here it is. Atmega 328 on a breadboard 8 MHz internal clock. That's the one we are compiling for. And we have fully compiled. João, uma bateria para isso aqui, ligar, só para ligar. Tem aí? Então. Okay, done compiling. I will now set up the FTDI so that we can program the drone electronics.
You change the.
Okay, let me just put it here. The message.
Deixa eu ver.
Não, tá.
Não tá aí, velho.
Tem aquela outra.
Vai fazer ali. So, for those of you arriving now, I'm going to describe briefly again the mechanics. I did it in the first part of the live stream, but I see that some people joined after I talked to them about it. So,
Era bom. Assim. Assim é do robô, né?
Jimmy. Yeah, lovely. So, let me just connect it here.
Eu acho que era o contrário.
O DTR, aqui, ó. Não é realmente assim.
Não. Não.
Yeah. So I want to change the camera, not to this to this camera. So yeah, this is our drone, and here we developed it in SolidWorks. I showed earlier the part. The live stream will be started on YouTube, on Ivan YouTube channel, so you can go there and check how you arrived at this final version in SolidWorks. Yeah, this was made in a MakerBot applicator. So this is 3D printed, and you can 3D print it in like 1 hour and 50 minutes, or 50 minutes, 1 hour or 1 hour and 10, depends on your printer. But it's pretty easy to print, doesn't need support and these other things. We've developed a board to the drone, the PCB, and it's only single layer because we want to keep the project the most DIY as possible. So yeah, it's single layer, and we have like an 80 mega 328. I think almost everyone have one these days, like in their Arduino or something like that. It uses an MPU 6050 IMU and some other things like a barometer and compass. All this is through IQC or R2C, what you want to call. And we have like 4 comms, and I always forgot the name, but in ESP8266. So the ESP is doing the comms, and yeah, it's this. Right now.
Oh, we're just setting things up so that we can program the electronics. We're looking for cables and stuff, so
yeah, we're finding cables in the room, so it may take long. But yeah, it's this. About the electronics, and yeah, we have 6 motors. All of them are DC motors, and we control them by using some regular transistors. It's a BC337 in this case, or a 617. Let me. Yeah, yes, no, it's a 637 regular transistor, just to control through PWM the power of the motors. So yeah, this is pretty straightforward. Yeah, this is the board. It's like full with resistor jumpers, and yeah, we tried to make, just as I said, the most DIY as possible. We're figuring out another version too that will be manufactured, but this is the one we're going to share on GitHub and share on other places so people can make their own. We're going to sell them in a Brazilian website, like just like Kickstarter. It's called Catarse, and and at the end we but we're going to make it open source too, because we like people to see people making things, and even drones. We think they're awesome. Yeah, just finishing the setup here. Um, I need to find the batteries to power up the drone so we can put not the drone but the board, because as it's in the description that it's in the, as we said earlier, we have a problem with the 1S cell lipo battery, that one cell lipo battery that we bought, and we can't fly the drone because we bought another and we are waiting for it to arrive here. And yeah, they are like cheap Chinese batteries and they don't work very well. So if you are planning to buy some battery like this one, don't buy it.
Cadê os cabinhos daqui?
Não, tem um, velho, que tá aqui na caixa de cabo.
Só tem um? Não tem mais dois?
Não.
Só pra ligar ele que tá direto. E aí, escreveu a bateria.
Eu tô jogando no lipo 7, velho. Não tá com lipo 7.
Não, eu já sei como fazer.
Se você tiver o lipo 7, dá pra ligar, pô. A bateria tá bem no lipo 7.
Pronto. Deu certo.
Tá aqui, ó. Já tá ligado, sei. Pronto. Deixa eu lipo 7, já dá pra ligar aí.
Não, mas eu ligo direto aqui, ó. Esse é melhor. Vou fazer um 2 para 2.
Isso aqui de cabelo, olha aqui, ó, a bateria dele.
Daqui, se eu for ficar muito tempo.
Uhum.
Bom, vou desmontar isso aqui.
Você tirou da caixinha de montagem aqui? Isso, tá do lado, do lado. Yeah, root killer. These Cobra motors are really better. We have a friend that plays with racing drones, and he has them, and they are really, really awesome. They are like really powerful, and yeah, I like them a lot. But if you look here, our drone has like not enough space for such motors, and we want to do something really small. And yeah, it's a simple design, and it's made to be cheaper. So I think we finished looking for cables and batteries.
Table.
So we are still going to make some adapters. Piscou. Deu certo. Ele piscou, deu certo. Yeah,
It's working.
it's working, it's fired up, so fire up the system.
Oh, everything is.
Everything is working, so status. You can change now.
So we have our setup now. Let's try to program it. Okay. Not working yet. Então, ao contrário mesmo, cara.
Não, tá, velho, tá certinho. Se deu certo. Deixa eu ver aqui.
Ah, verdade. Okay, so now we have our setup complete and tested. Let's check if the message is okay. Let's reset it.
Up.
Okay, so we are up. This is just to configure everything and be sure that everything looks okay. Let's continue on what we were discussing, the initialization. So the basic thing I will do is to create another file, and I call it system.h using Chumanchu orientation to use pragma once. That's a really cool thing. And here we will declare everything we use, and in the system.cpp we should implement everything. And one thing that you should know is that even though those files are kind of linked, you should always include the .h on the .cpp. Also, I like to include the configs and also anything that is miscellaneous. Okay, so those files in the top. So here we will implement a method called a function called system underline init. It won't receive any arguments, and inside here it will do this IO setup. Okay, so it's inside the system that will set up the pins and everything. Going through the hold hardware, I will be declaring also the pins. I have the datasheet for our hardware here. So the LED is in the pin number 8. I like to put pin before the things instead of this because it's more maintainable. If you define, for example, buzzer, you won't get like buzzer pin. It will be pin of buzzer. So it's a more logical thing that I use. I like to use 2 spaces between each block of code inside the same file. Let's define I2C setup. We will use I2C for the communication between the MPU, the IMU here, and the drone. So let's define the I2C speed, which is in our case 400 kilohertz. And also I have a snippet here to initialize the pull-ups in the I2C port, and it is defined I2C pull-ups enable. This is got from the internet. It basically set up the port to be an input with pull-up and it will basically set the pins A4 and A5 to pull up. Okay, going on, now we can define the more specific things about the MPU. In this case, we are using the MPU 6050, and let's define the address. So IMU underline I2C address is in 0x68. If we open the datasheet for that, we can see that it's the default address for the MPU. Here's the page. And here's the datasheet. So abemos datasheet. Let's see the address. Probably the first one that I skipped. So it can be 0, 1. Where is the address? So here is the address in binary. And here is the address 0x68, and that's why we placed it 0x68. I want to show you everything, not just put things here without knowing. And well, this is our definition for the IMU. And now let's define our motor inputs. Okay, something that I like to do when we have multiple boards, there are one after the other, like pins for the motors, there are 6. We could define like motor pin 1, motor pin 2, motor pin 3, motor pin anything else. But that would be a problem because basically when you want to iterate for everyone, you wouldn't be able to. You would have to write everything multiple times. So I will do in this way, okay, and then show you how I like to do. So the motor pin 1 is 9, 2 is 6, 3 is 5, 4 is 3, and 5 is 11, and 10. Notice that all those pins are PWM, okay, and this is necessary so that we can control the drone. Pass 3, 1, 2x, okay. So here we have 1, 2, 3, 4, 5, 6, and here is how I like to define it. In this case, motor pins, it's array, and we define it as a constant so that we won't need to change it, okay? So this is motor 1, and so I'll copy this thing here and place it here. And we need commas here. Okay, so this is basically the pin name for this, and that's all we needed for now. In system init, we will initialize the communication of the drone, and also let's initialize the pins before it. In this case, pin mode of the pin LED goes to output. Okay. Initialize the serial, and then anything else goes here in our start message. That's okay. But there is also something that we will start using a lot from now on, which is the library called Arduino Thread. It's a library that I made to work with projects for Arduino. It's really simple. If you talk to me, oh, but that's not real threads. Yeah, that's not real threads. But they help a lot on organizing your program. Okay, it doesn't consume a lot of time, and it helps maintaining and organizing your code pretty much. So you can go to this link here. I'll post it on both chats, and you can download it and read the documentation. Okay, and basically what Arduino thread does is to organize your code within functions. Okay, so one thing that we need to do before understanding this is that our system init won't work yet on the Arduino here, and that's because even though we include the modules, in our case the system.h, even though we include it, the method won't exist. As you can see, system init was not declared in this scope, but it was implemented. So the problem here is that our method is not declared in the system.h. So let's go there and just fast forward declare it, so that when it compiles, it knows it needs the system init and it is in the header file. Okay, not declared yet. Why not? Void system init. Should work. System is needed. Though. Okay, it should work now. So system init is not declared yet. Whoa, I typed it wrong 3 times. How can that be possible? Okay, output was not declared in this scope. And why is not output declared in this scope? Because when Arduino includes a file, it doesn't include the Arduino itself. Oh, so what we have to do is include arduino.h. But as you can see, it compiled. So it was missing, for example, pin mode or anything Arduino related. Okay, so every time you use Arduino functions, remember to include it in your file. You don't need that in the .ino file because it includes for you automatically, but any other file that we include, we are going to use it if we use any Arduino related method. So this is our module system. That's okay for now. And let's start using the libraries. So I will create a space here for the libraries. And let's include Arduino thread.h. I don't know the difference pretty well about the minus and the double quotes, but I like to use double quotes in custom files, so config, system, tarana, and minor and greater with libraries. Okay, so we can differentiate it. If you know the difference, please explain to me, because I have never stopped to look about it. It just works. So Arduino thread, it's basically a library that holds functions with timed actions. Okay, so you can create a thread. A thread is an object. You can create it as a pointer as well, and you can set, if it is enabled, set the desired interval to run that thread. So let's imagine this example here in the loop. Okay, so you have, let's say, a function do something, and you put a delay 10 here because you want it to execute every 10 milliseconds. Okay, so do something is something that you want to execute every 10 milliseconds. And imagine if you have another method now that is called do another something. Okay, but do another something needs to be run every 20 milliseconds. So, whoa, that's a problem. You could put a counter here, count, which is equal to 0, and count plus plus if it count greater than 0 or greater or equal than 1. you execute basically the rest of the division for 2 is equal to 0, then execute something. Or another easier way of doing it is doing something 10 milliseconds and then doing another something, and in this way you have do something every 10 milliseconds and do another something every 20 milliseconds because of the both delays. But the problem with that is that if you add more and more methods, each one with different timing, you will get in trouble because you want you have problem to define a way of running this thing in a generic way so that you don't have to change your loop. Okay, so the way things work in bigger applications is that you time things. Okay, so I'll put an example here. In this case, I will create a long that is called uh, um, last time it was executed. It's a big method name just for example. And here we check if here we check if the time passes, the passed time. Okay, so there is a method for the current time in the Arduino which is called millis. There is also microseconds, but millis is reads the milliseconds since the Arduino was turned on. So if you check if milli is greater than 1,000, okay, you are checking has the Arduino been running for more than 1 second. This is what it is asking. Okay, but imagine that if that we subtract that from last time it was executed. Last time it was executed, it's a complex name, but the value is 0. So millis minus 0 is the same as not subtracting. And that would give us 2 millis is greater than 1 second. Okay, but let's continue with last time it was executed so that you can understand. And if the time passed since the Arduino was turned on is greater than a second, then do something. Okay, but when you do something, you want to save when you did that something. Okay, so when you finish doing or you start doing, you can save the time it was when it did that something. So let's put this inside here. And what this simple code is doing is executing every 1,000 milliseconds the method do something. Okay, and this is a pattern that you can duplicate but with different method names. Okay, and you can change the time for each one, in this case 10 milliseconds and 20 milliseconds, and you can work with multiple methods simultaneously. Of course, it's not simultaneously because the Arduino can only execute the instruction at each time, but it seems like simultaneously because the loop taken here to check if this should be run, to check if this, to check and that is really fast, in the order of microseconds. So you can put as long as many as you want, and you still have many programs being running simultaneously. Okay, the problem with this that we must know before starting to code our firmware is that if in do something we put, for example, a while true, you will never get out of this method, which means you will never get out of this line, which means do another something will never be executed. So that's a big problem. Okay, that's a big problem because you don't want things to get stuck in your code. You want things to be smoothly and running. So you will never place anything that takes more than, I don't know, 1 millisecond in any function. That's something that you need to be sure, because if you put a delay of 10 milliseconds here, then you will fuck your code entirely. That's the word, because you are delaying 10 milliseconds here, and you will propagate that time to every method, and that's really bad. So if you want to delay 10 milliseconds and execute another thing, what you actually do is create a thread that will take 10 milliseconds to run, and then you execute that thread. But you never use delay. Never. Okay? So just to be on the same page, never use delays. Let's put it here in Illustrator so that we can make sure you never use delays. Let's open Adobe Illustrator. Okay, opening. And I'm thinking about creating a t-shirt for that. Never use delays. Okay, Illustrator is taking too much time to load because I'm streaming. Damn it. Okay, Illustrator is open and it's fucking slow. New. That's how you do it. You create a new one and you put never use delays, and you increase that to the size of a huge thing, and you put bold on it. Regular, no, italic, bold. Is there anything? Yeah, and you put red on that. Okay, never use delays. Okay, now you can close Illustrator. Going on, let's simplify this with the library I have just told you. Instead of having methods and variables to save the time it executed, let's have the thread object. In this case, let's define it as do something thread, or I don't know, thread that does something. This is only an example, okay? And what this thread does is execute do something every 10 milliseconds, okay? And do something must be declared before thread. So parentheses here, this is a tip. I need to put do something before, because if I declare do something after, in this line here, do something is not declared. So if do something is not declared, sorry, I have placed it wrong here, it's thread only. If do something is not declared here, it will throw an error. So let's see that error. That's another error, but that works fine. Let's just clear everything here. So, okay, crashed my face. It doesn't throw error. But if I execute that, for example, inside loop, and it's a bit after this setup, I had problems with this. Are you kidding me? Okay, so I'm dumb. Forget what I was telling you. I would say that you can define the method before. Forget. Anyway, you define the thread here, and the interval, and the method that will get called when you call that thread. And that thread has a method called should run. And it basically returns true if it should run, okay? So if it should run, then run. And this method run encapsulates the running of the method you defined in the instantiation, okay? Oh, but I don't know the method yet. Can I declare it like this and then set things up? Yes, sure. Try do something dot set interval to 10, and on run you should do something, okay? So basically we did the same thing with more lines of code. I prefer the other way, but this way is also used. And okay, we have simplified that thing that we made with using midis. inside it should run, it actually checks with millis and runs, actually runs the thread and resets that last executed time. And we can do it for many threads. Okay, just declaring another thread here, thread, do another thing, thread, let's place it here, and void do another thing. It doesn't have to be anything related with the name, but this one I want to execute every 20 milliseconds, and I can check it here and execute it here. But that's kind of dumb, because if you add another thread here, you have to add it in 2 places, right? The declaration, the setup, and the loop. And that's off by 1 error because I said 2, so 3 places. So that's why Arduino thread has another class called thread controller. And thread controller is basically a thread that holds multiple threads that you created. So let's call it CPU or maybe system. Okay, system, it's okay. So let's call it system. And inside the setup, we can put like system.add. So I'm adding a thread to it. I want to add a thread do something, and I want to add a thread do another something thread. Nah, do another thing thread. So I'm adding 2 threads to the same controller, and this is really simple to do. The reason for the E here is because the thread object is not a pointer, and actually it is a instance. Okay, so you need to pass on the location of that object, not a copy of it. And inside the loop, instead of checking for everyone, you only run the system. Okay, so inside it, it is running the thread of the system. In this case, we don't run anything, but I could do system.on run, execute this, and also running every other thread that is inside if that thread should be run. Okay. Oh, line 23. Dang. Thread. Okay. Where? Yeah. Thank you very much for fixing my code. I have to change it here as well. And this one do another thing. Thank you very much, root killer. So in system, in the loop, we will only have this this method here, because it will automatically run what should be run in the time we need. Okay. Just to show you that it's really simple. It's a really simple library. Let's go to the Arduino thread and open the thread.cpp, and you can see that the run method, for example, checks if you set it the callback and it runs, and then it calls this method run it, and inside it saves the time, okay, and it caches the next run so that we don't have to compute that every single time we loop through the thread. And the should run method, where is the should run? Okay, here, basically does that that calculation. Okay, there are a few things here so that we don't extrapolate when millis goes beyond the limit and overflows. But basically we returns if the time remaining is less than 0, okay, and it's enabled. So the thread has an enable flag, and if we go to system and we, for example, inside a thread we do a thread that does something, which is the other thread dot enabled is equal to false, it will stop that thread from running. so this method won't be called again, and you can enable it using this flag here. So it's a really simple library. You can use it with multiple projects. I use it all projects that I do, and that's basically it. The thread controller here, so that you can see the run method checks if the thread has a run callback, and it runs, and it goes through all the threads, checks if that thread should run, and runs it. So basically we do we iterate every thread inside the thread controller and run it. That's what we have done in the loop, and that's what Arduino thread does. Okay then, so let's continue with the drone coding stuff. We won't declare threads here, okay? We won't, because I want things to be separated, okay? So we should put the thread of the system in the system file, right? And that's why in the system.cpp, oops, I will declare my thread controller called system. Okay, this system thread won't have a callback, okay, but we will use it to put things on it, and all the program will also use the same object as the root of all our programs that need to be executed with a periodicity. But if we do this and we try to access system on the init file, the main file, we may notice that system was not declared in this scope, and that's because we didn't declare it in the system.h. And the problem with putting system thread controller system here is that you are actually declaring system again. So the compiler will say, oh, you are redeclaring this, or doesn't have a name. Okay, it doesn't have a name because we didn't include the thread controller, and also let's include thread.h. So even though we have the included file, redefinition of thread controller system. So basically in the H, when it's object, when it's a variable, you don't do this. You put the extern before the declaration, so that the compilers know, oh, okay, it won't be declaring this right now, but I know it exists, okay? Okay, so it's working our code. We have two things inside system.h, and what else should we put inside the system.h? Let's begin with the pretty basic thing that everyone does with an Arduino, blinks a LED. So just to know that we are actually alive, that our controller is running and the things are at least in place. So let's create here a thread heartbeat. I'm from Vitória, Espírito Santo, Win, answering the question. But I live in São Paulo for 2 years, okay? Continuing, this thread heartbeat will run the heartbeat. I will call back. That's a parent that I use. And this heartbeat callback is a method, the function, that will basically make the LED blink, okay? So digital write ping LED. I could put here high and create a flag last state is equal to false. or maybe a bool. And if let state is equal to false, I will set the state to high, and else I will set the state to pin LED low. So let's stop a bit here because this is pretty dumb. If you code like this, it's not that you are dumb, but you don't use C++ as it could be used, okay? So let's think about here. If let state equals to false, let's invert this thing, okay? I want to check it for low, for true, truicity, if that word exists. But checking if it's equal to true is the same as checking if something. So we don't need the true here. If let state is the same as is let state true, okay? But also, if it's true, then set it to low. If not, set it to high. And then we should invert that state, right? Let state is equal to false and let state is equal to true. And that's a pretty complicated code. I will simplify it to one line in a minute, but let's continue on. First, I don't want it to set it to a fixed value. It's the same thing that I would do here. I put a not and let's state. Okay, so this exclamation point inverts the state, the variable. So if it's true, it became false. If it's false, it became true. Okay, but then we can say, okay, let state and low, they are linked. So if let state, then low. If not let state, then high. And if you go to the Arduino software, the firmware, you see that high is basically 1, which is basically true, and true is basically 1 as well. And that low is basically 0. So they are the same. If I put 0 here, it's the same. Okay, if I put false, it's the same as 0. And let state is what we want to set in digital, right? No, we want to set the inverse of let state, right? So we don't need that if anymore, and we simplified it to this. But it's also 3 lines of code that we don't need. So what if we, instead of getting the state and inverting the state, what if we read the digital value of the pin LED and invert it? So if it's outputting high, it will return true, and you will invert to false, and you will turn off the LED. If it's outputting false, it will invert to true and turn on the LED. So we don't need this anymore, and here is our linking. Okay, any questions? This is something that is really simple to do. Okay. Well, let's set up the heartbeat. So heartbeat.set interval, I want it to blink every 500 milliseconds, and heartbeat.onRun, we have a spelling error here. I want to run the callback. So every 500 milliseconds, heartbeat callback will be called, and my LED will change its state. I don't need this anymore. And let's try to compile it. Okay, heartbeat callback was not declared in the scope. Yeah, I knew it was. My bug existed. What is happening here is that heartbeat callback is not declared because it is declared after we run it. So the C++ compiler is dumb. It doesn't know it will be declared. So it says, okay, it doesn't exist, so I cannot continue this, and blah, blah, blah. So what we do with it, so that we don't have to declare the less important thing before the more important thing, in the case of system init, is more important than heartbeat callback. That's why I like to put it before. It's not a rule, but it's a pattern that I use. You can use the fast forward declaration, so that your program knows that this exists and it can continue to compile, knowing that it will be declared further. So fast forward declaration. Just put it here so that you can search it on later. And let's try it out. Okay, it compiled. But there is a big problem if we upload this code to the Arduino right now. You see, it won't blink the LED. And the main reason why is because the system thread controller doesn't consist of the heartbeat thread. So add threads to heart to system. So let's go to system.add, and I want to add the heartbeat. Okay, and this now, as you can see, let's upload this program to the okay. I wanted to zoom. I cannot zoom it manually. Okay, so we have a blinking LED. That's the first sign of life of our drone. That's pretty simple for 4 hours of streaming, but I hope you are learning a thing or two. I appreciate the feedbacks if you have any. Let's continue. My face is really ugly, so let's continue with the video of the cute flashing LED. Now that we have the heartbeat running, we can do stuff. Okay, so continue on with the system. Let's put the communication here. Okay, not the communication with the drone that controls the target attitude, but the communication from the serial, so that we can debug and set things up. So let's create another thread that I will call serial. Serial, I don't know, serial, a good name for it would be serial debug. It's debug related, so serial debug. Setup, serial debug, set interval. I want to check the serial every 10 milliseconds, and when it checks, I want to run serial debug callback, which is a method, a function, or whatever you want to call it, that will check for the serial. If not serial available, okay, so if serial available, the number of bytes available in the serial is less than or equal to 0, is the same as not serial available, okay, then return. I don't want you to do anything, because if you try to get a character, incoming byte from the serial, and there is any, it will hang our code. So remember the delay problem. Do not use delay. You cannot do serial.read without knowing there is something available. Otherwise, it will hang until there is something available. So the char here, the char that I will call command cmd is equal to serial.read, and then we do like, okay, log, hey there, input, and then log again the command, and then log again line breaker. So this is our debug.
what is missing here is to fast forward declare it as well, otherwise we will have the same problem. And also add the thread to the system. So we have two running threads, right? Both things happening almost simultaneously. Okay, so we have a problem because we are using serial here, but has no member available. Okay, that's a spelling mistake. Available. That should fix it. And that fixed it. Let's eat some chocolate. Okay, so it's running. Let's turn it off and turn it on. It's up. Let's send a character. Hey there is an input. Let's send many characters. And you see that hey there will be printed multiple times. And the reason why is that each time it runs that thread, it checks if it's available and it gets only 1 byte. So here's our code running. And now we can, I don't know, check for the command, and here will be something like if command is equal to, and note the simple quote here, not double quote. I don't, simple quote are only used for characters. So this is basically the ASCII value character of the ask value. So if you put in hexadecimal, I don't know which value it is, but if you don't remember, you can use a single quote, okay? In this case, if the guy sends, I don't know, P from ping, it will send a ping back. Log ping back. Okay. Any other thing, it won't do anything. Oh, this is useful. We will use it for debugging. Okay. Manipulating. It's running serial monitor. The reason why the app isn't showing here is because the Arduino doesn't reset when I open the serial port, okay? But if I turn it off and turn it on, it will show the message. Or should show the message. Why? Okay, turn on. Where is my app message? Is there a ping? Why not? I want my ping. And I want my message. Let me reset everything. Okay. So P. Okay, it's up now. Ping back, ping back. If I send anything else, it won't do anything. P, ping back. So it's working. Let's just put this character here to be more cool and go on. Okay, so system is initialized. You may ask about, oh, what about the motors? You didn't set up the output pins for the motors. And the reason why is because I want to put the motor setup and the motor control in a different module. We call it motors. Oh, that's not obvious, you know. So let's go there and continue with our initialization. Okay. So let's make the motor setup. Let's create the motors dot h and the motors dot cpp and use pragma bonds. And in CPP, let's include the configs and also include the motors, and also between them include the libraries, in this case thread.h. We only use thread here because motors will be a thread only. And let's do this initialization in a different way, okay? In this case, I won't be using a method, a function, like we did in system, just to show you different ways of doing the same thing. In this case, I will use a class, okay? And this class will be called motors, and I will have a public method that is a static method that is init, okay? And init is a method to initialize the motor. In motor.cpp, I have to implement all this, and the implementation of classes are done in this way. You set the return. It's like declaring any other function, but you define where that function is stored. In this case, is in motors, and you put 2 double dots here, and you put init, and then you declare the method. So let's see if this works here. Let's include motors and do the initialization. I'm not using a dot here because it's a static method, so double two dots, it's to access it init. So two ways of doing the same thing. Okay, let's see if it compiles. Okay, I have. Okay, I didn't define the return. Okay, now it should work. Expected is expecting someone here. And now we have a compiled program. So let's do it for now like this, and you can choose the best one. The good thing about using classes is that you don't have to use methods for underlined methods for organizing your program. So in this case, let's say you have static void set power of motor 1, motor 2, motor 2, 3, motor 4, motor 6, and motor 5. So you won't have to create methods like motor slash set power. You can use it more cute with motors set power. Like set power is inside motors. Okay, if you compile and see the difference in size, you notice there is almost no difference. Okay, we can do this here, but it will take time and I don't want to focus on that. So let's just use it like this. So set power will set the power of all the motors, so the PWM value, but the power won't be a value going from 0 to 155. It will go inputs M1 to M6. It will go from 0 to 100. Okay, so input is a percentage value. And let's implement that method here as well. Motors slash two dots. Okay, so let's initialize our motors. And basically what we do in the initialization of every motor is to set the pin mode of motor pin 1, motors pin 1 to output motor pin 2 and go on. But there is another cool thing about what we have, how we define the pins in our defines here, that we stored every one of them inside a array, and I will show you how to initialize all of them without having to copy and paste multiple lines of code. And as I don't remember how I did that, I will go to my Google Drive, no, Dropbox, here, here. So, okay. So here is how I like to do it. I put all the pins I want to initialize in the array, and then I loop through all of them and go setting the output mode and so on. So let's implement this here. You don't need to do this, but it's a cool thing to know. In this case, output is actually our array of pins, so it's motor underline pins. Let's check that. Motor pins is our array with 963. It's an array of integer. So basically this will initialize all the pins as output. And in the end, let's do a motors set power 0, 0, 0, 0, 0, 0. So stop all the motors, please. So in set power, let's assume that all the powers is an array, and we have the power stored in order. Okay, so if we access power 0, it's actually the power of the motor 1, motor 2, 3, 4, 5, 6. Okay, and let's go through all of them now. Let's iterate it. So going from 0 less than 6, e plus plus, oops. And what we will do is to convert the power of the motor that goes from 0 to 100 to go to a 0 from a limit that we want. Okay, so in config, let's set the limit for all our motors. Which is motor power limit. Okay, but there is a problem with this, because we also have a limit that is minimal, which means if you set 5 to the motor, it won't be able to rotate the propeller. So we could do like, okay, if you set 5, then put a minimum of 20 so that I at least continue to rotate the propeller. So the limit will be a max value. In this case, we can place it 255, and also power minimum, which is the minimum value. I will put 20 here, but that would need some testing. Okay, you go increasing the power until your motor rotates, and that's your minimum power. And what we will do now is to convert that power that goes from 0 to 100 to go from minimum to maximum. Okay, so continue. We will have a temp power which is equal to the power at the index I multiplied. Wait, let's think a bit. So it will map 0 to 100 to min to 2255. That's it, to max instead. Oh, Arduino has a method for that. Oh, I love Arduino. Okay, let's go to the reference, and there is map, a method for doing regra de 3. It's called map. Oh, where is map? Where is map? Map is here. Map is here. So map value from high to low to high. So you map X that goes from 1 to 50 to 50 to 1. So invert it. So map is a really cool function. You can look at it in the reference of Arduino. And let's go on. So using map, we can map the value. Map, look at it, powers I, going from 0 to 100. I want it to go from, I will diminish this method name because it's really big. I want it to go from minimum to maximum. Okay. But the problem here is if you set, for example, 200 in this, it won't limit the returned value to minimum and maximum. So let's make sure that the temporary power that we are calculating goes from minimum to maximum. So let's use the method max. Sorry, let's implement this in a good manner, and it's a good tip as well. So you could check if temp power is less than 0, not 0, it's less than motor power minimum. If it's less than that, then the temporary power value is motor power minimum. So if you say it's 20 the minimum and the calculated value outputs, I don't know, 10, then it will be true and it will set to 20. So it's a minimum. And you could do this as well with the maximum. And that would solve it. But that takes 2 lines of code, and there is a simpler way of doing it. It won't consume less or more time to compute it, I guess, but it's more easier. You can say that the temporary power is equal to, and then you put this if here. If temporary power is less than then it's equal to motor power minimum. Otherwise, sorry, this question mark checks if this is true, and if so, it it returns the value from the next statement. Otherwise, return the self value. So this is basically in English. Is the temporary power less than motor power minimum? Yes, so set it to motor power minimum. If not, then set it to temporary power. So you won't change temporary power, setting temporary power to temporary power. And let's duplicate this and just change to greater than max and change this to max. And then we have our value being limited positively and negatively with both limits. And also, if the user sets the power to a negative value, I want it to shut down the motor. And that means do not turn on the motor, okay? So when we do 0 here, we are doing it wrong, okay? Because 0 will set the power to 20, because 0 maps to the minimum power, which is 20, and that's the problem. So when we do 0, we are doing it wrong, so let's do it last one so that we can set the power to low completely. So digital right, not digital, analog right, motor pins I want to set the analog value, the PWM value to this, and temp power with temp power. But we only want to do that if the original power value, which means the input params that the user wanted to set to the motors, is greater than or equal to 0. So if you set the power to 0, it will set the output power to 20. If you put something that is less than 0, like -1, then I want it to completely shut down the motor with low. Okay, so this turns off the motor. That's basically the power the power part of the drone. In the case of a drone that does not use a DC motor, the analog right value would be something that ASC, which is a speed controller, can read. So this is where you map things for something that can be output from the microcontroller. And it doesn't matter if you're using a DC motor or a brushless motor. What matters here is that you will be outputting the power from 0 to 100 to whatever you are using. Okay? Yes, I'm hearing an echo in my string as well. It doesn't matter if you're using a DC motor or oops, I had a video playing on my computer, so sorry. Thank you. Let's make a pause here for questions, and I need to get something to eat and drink. Any questions? 5 minutes. So let's make pause here. We are not done yet. It's just pause. We are just doing that. Okay. This OBS program is awesome, but it's consuming my whole CPU. So we are in pause. Let's put a message here. Pause at 5 minutes. And
Aí quando você passou, etc.
da hora isso aqui.
Uhum. Agora você fala, agora eu vou fazer aqui e vai fazer o heartbeat aí. Como a colete funciona, então a colete funciona com mais.
Não, vai pra queimar.
Tomara que a colete funcione, tomara que a placa funcione e eu deve parar e falar, mas tô errado. A gente arruma pra fazer e aí arruma tudo. Ninguém escrever isso aqui. Tá mutado aqui?
Onde?
Não, lá ele já chegou ali.
Oi?
Então, eu tô chegando já.
Conseguiu terminar a placa?
Uhum.
Vamos ver se ele liberta.
Comenta aí embaixo pra ele. It will if we stop missing your classes. It will. We just need to miss more of your classes. Marca ele?
Como que ele escreve a carinha?
Killer. Ele não fez a conta de 3 carinhas.
O que é isso?
3 carinhas.
Eu descobri um negócio no OBS. Olha aqui.
O Sand Changer.
Quando você põe uma. No Mac pelo menos. Tá vendo? Image 1. Quando eu põe pause. Não. Cam. Video capture. Oops. Olha. Se eu Tem video capture, tem que ser 920. Mas aqui, por exemplo, tá video capture device. Se eu tirar esse video capture device, eu consigo botar tipo o mesmo daqui, entendeu? Já tá salvo. E aí ele não fica processando 1 milhão de vezes. Sabe?
Mó legal.
Tem que mudar isso agora em todos.
Uhum. Depois a gente vai no capa mais tarde porque deu vontade. Terminar aí no jogo.
Eita,
E aí de ontem você chamou.
bota o pé.
Touch face.
Já tenho 12 likers.
Tá se ele falou quanto de vezes que tinha gente em português, que não tá.
Tinha o quê?
Se ia ter em português depois. Vai fazer depois, posta no YouTube, agora faz em partes, e vai postando tipo vídeo por vídeo, sei lá.
Isso é uma boa. Mas o YouTube tá dois português.
Uma bosta. Não sei. Tipo assim, aí tem algo tipo I'm now going to turn on o babuinho.
Okay, so we are back. We have finished the motor part, but let's make something that will help us, which is a stop method. And it's just to simplify when we want to stop and not to set the power, okay? And basically what we do here is to use this line of code and stop the motors. And instead of placing a negative number, we just use stop. That's okay now. So let's continue with our script here. So we have implemented the motors. We may test it now. So let's put some debugging in the system.cpp. Check if the command send is 1. And if so, let's go to motors and set the speed. Set powers or speed? Power. Something good is to know the difference between power and speed. power is the raw value that we set to the motors. Speed is the actual speed, maybe the angular speed, the linear speed. But since we are not controlling our motors with feedback from encoder or something like that, we are setting the power of the motor. If we had a control that controlled the speed of the motor, then we use speed, just so that you know the difference. It confused me sometimes. So if we set to 1, then I wanted to go to 50% of power. Let's put it 20. If you set it to 2, let's go to 60. And if you set it to 0, I want you to stop. Okay? You will see an error while compiling because inside the system, motors do not exist. So we need to include motors here. Okay, so set power. Oh, I'm really dumb. I need to put all the motor powers. 4, 5, 6. 6, and that should work now. Okay, so let's see if that works with a simple profiler, and let's hope that it works. Okay, that's 20%, and this is true. Oh, my motor is not stopping. We have a problem here. 20, 20, 20, 20, 20, 20, and stop. Let's debug this. How do I stop my motor now? That's not cool. Reset power, please. Okay, so we reset the power, and let's try to figure out why it's not working. Set power. Let's debug this. Log powers. And let's print the output power with iSpace. And in the end, let's print slash Havain. And let's see what's being outputted to the motors. Okay, done uploading. So let's send the one command. 67 seems okay. 2, 67, 0, 67. So we sure have a problem in our map. And the reason why we have 67 is that I don't know yet. Just a minute. Sorry, I got a call. So going back, we have the temporary power. And it's mapping. So if I set 20 map power, it should work. It's not working. So let's see what is outputted from the map so that we can debug. Okay. So the problem is in the map method. Unless, of course, we did something really dumb in here. Okay, let's send the command. Okay, here is the problem. Fucking equal. So if command equal 1 is the same as if command equal is the same as if 1, which is the same as some hexadecimal, which is the same as if true, which is true, so it will always set the power to 20. The problem is not in the motor part, it's in our debugging part. So let's move on. Remove this and this and okay. So let's send the command. 1, 2, 0, and shuts down. 2, slow, 0, shut down. Okay, so we have it working. We can test it with other motors, but it's the same for everyone. 1, 2, 0. So that's okay with the other ports. Moving on, we have done the motor part, and the next part is the let's make the IMU part. Okay, this is more a hardware part, and for each drone it will be different. So the implementation here will use the MPU 6050. So let's create a new file called imu.h and also on imu.cpp, and we want to include the wire library, which is used for I2C. We want to include thread, and we want to include this library here. Where are you? MPU 6050 and this MPU 6050 6-axis motion apps. And the reason why we want to include that instead of the MPU 6050 only is because this library will upload the code to the IMU called DMP, which is Digital Motion Processing. And that DMP code will go into the controller, the microcontroller inside the MPU, and it will continuously join the gyroscope, the accelerometer, and in the case of better AMU, the compass sensor, to return the Quaternion. If you don't know what Quaternion is, you can search on Google or go back into the beginning of this class. We talked about how Quaternion works and the yaw, pitch, and roll. Okay, so basically, this is the library that includes not only the basic usage of the MPU 6050, but as well as the digital motion processing. There was a problem when I included this file in an included file of the project, in this case IMU, and the problem is that the library wasn't written following the C++ rules. So this file here that contains the MPU program, it was implemented in the same file, in the header file. So I couldn't include that in both places at the same time, and that's pretty dumb. So what I did was separate to the implementation and the header from them. I didn't send a request to a pull request to the library in the GitHub, but I may do it soon, okay? Because that's pretty a pain in the ass. So let's continue. Let's include also, oh, we have included thread, so we don't need that. Let's put this on the header and put Pragma once, and let's define our class. In this module, the IMU, I want it to be different, okay? So I don't want it to be a module, but instead to be a class. So you call it IMU thread, or maybe only IMU, okay? I'm working on my homemade robots with Rust. Look, it's just moving planar and not 6 degrees. Luckily, it's just moving planar, not 6 degrees. What do you hide? Shape and by moving planar. So this IMU class, it's not like the motor class that we implemented. In this case, it won't be static. We can create as many as we want, but oh, cool. In the case of this class here, we will incorporate or abstract the MPU class here. If you want to know more about this class, you can just go MPU 6050 GitHub Arduino, and you will see what I'm using here. This is the file. As you can see, it doesn't have a CPP file. So anyway, this file here, it's a big library that contains many other sensors. Anyway, let's create a private field that will hold our MPU 6050 object that I will call MPU, and also a boolean flag that will say if the DMP is enabled or not. Okay, just answering a question. Let's see, because it told about. Oh, that's Nightshade. Anyway, this flag will say will be our flag that mimics if the DMP is or is not enabled. Okay, so is the DMP in MPU enabled? And why I like to do this is that with this MU, if you don't read the data inside it, it will overflow and that can cause trouble. So every time you stop reading the MPU with a period of more than 3 or 5 milliseconds, 9 milliseconds, it will give you trouble. So you just stop the DMP from working, the program inside the MPU from working, and that seems to work for me. Okay. We also need a packet that will save the last saved packet. The packet is like everything that the MPU, the MU, returns us, and it's an signed int of 8 bits. And we will store 64 bytes for it. We also want a counter for the FIFO, which is the current value of the FIFO inside the MPU. We can do some caching of that so that we don't read how many bytes are available every time we check it. But it's a good thing to have. And also a flag to store the interruption status, but we don't need to put that here. Also, in this class, we want to have a Boolean flag that will say if we have new data or not. This new data will be updated to true every time we read new data from the MPU, which is valid. And every time we consume that information, we set it to false so that we can check if there is a new data in the IMU and not continuous compute the same data again and again. We will have a method called IMU, which is the constructor of this class. It will get called once we instantiate it. And also we will have a init method which will initialize the MPU and send all the program that the DMP needs to the MPU. And also this is a class that needs to be run every 8 milliseconds. And what can we do if this class actually is seen as a thread? Remember the thread class? If you don't, there is a link in the chat. You can ask me, I can send you. But the Arduino thread also permits you to implement threads, custom threads. Okay, so let's implement or extend this IMU class to a thread. Okay, so you put it like this. It's extending thread in a public way, and what we will do here is to override the should run method. Okay, And the should run method, if you go to the documentation of the Arduino thread, where is Arduino thread? Here. You can go to thread.h and you see that should run is an unsigned long time. Okay, so unsigned long time, and here is where we will check if the thread should run, but in a different way than we did before. We will check for time, if the time has passed, and also if there is a packet available. Okay, so we will go to the MPU, check if the FIFO buffer has at least 42 bytes, if I'm not mistaken. If that value reaches that amount of bytes, then we return true, so that the thread gets run. So we do it in two parts. Okay, checks if the thread should run time and enabled, and also the FIFO count, FIFO buffer. That's mainly it, and we just need the last method, which is the run method. Who will call both this method won't be us, it will be the system controller thread, and the run method we override here. So basically that's it. Let's now put this class to, let's implement instantiate IMU now with the name IMU in lowercase. This is the IMU that we will implement inside the IMU.cpp. So we are implementing the class and using it in the same class, in the same file, but that's okay, we only use one IMU. Anyway, let's now begin to implement the IMU. We are going to need this. We are going to need the configurations. We are going to need the system, and that's what we need. So let's implement the first method, which is the constructor. And what it does is to call the thread superconstructor. But we don't need to do anything here, and I don't counsel you to call init here, because you may do that init inline in code when you declare the class, and maybe the configuration is not ready yet. I will get this initialization from another file that I have here. I won't go through it every class, every bit, but here is the code. Let's log the initialization. Let's begin the I2C, initialize the IMU, check the connection, and if the connection fails, we return false. Set the DMP enable as false, reset the DMP, reset the MPU, set sleep enabled as false, so we activate the MPU, initialize the DMP. This takes some time, like 1 second or 2. set the gyroscope offset. I know this because I have tested mine, so I have discovered this. You can read some values and go updating this so that when the DMP starts, it doesn't take so long to stabilize. Okay. Dev status. If the status that the DMP returned is not 0, it means it failed. Okay, so we return it as false. Okay, DMP enabled is equal to false. Okay, dev status, I don't need this. And here we return true, false. It means we don't have initialization successful. So this is the initialization of the IMU. Okay. What we should do now is to override the Boolean method IMU should run. Okay, and in this case we are using a signed in long time. And what we test here is basically what this code needs to do is to turn on and turn off the DMP automatically. I don't want the DMP to stay on if this thread is not running anymore. Okay, so if we land the drone and we stop the MPU, even though we don't use that part in code, it's really important to do because sometime you will need it. Okay, so basically we are going to check if the state of this thread, and the state of the thread is the enabled. If you remember well, this thread.enabled, this means is the thread enabled, should it run? And basically if the thread is enabled but is not is enabled and the DMP enabled, which is the boolean that we created inside the IMU class, is not, we should shut down the DMP, right? So it's like MPU dot set DMP enable, and remember MPU is actually the object that we initialized here and here. Okay, so this is the MPU, and what we do here is set the DMP enable as true. So we turn on the MPU. So okay, and also the DMP state now will be true. But if the state is not enabled but and is I'm confusing myself. If the thread is not enabled but the DMP is enabled, okay, then we should turn off the DMP, and that's where we set DMP enabled to false, and we log the same thing as here. Oops, but that is false, and we set that the DMP is now off. Okay, so basically what this thing does is turn on / off DMP, digital motion processing. This part here can be changed and improved. So basically what we are checking here and here is if the enabled and DMP enabled are different. So if enabled different than DMP enabled, we should switch the state, and the state is the same as the enabled value. So enabled, I would enable the DMP with the enabled value. So if the thread is enabled, DMP will enable it if the DMP enabled was off. Okay, so that's the idea. You are enabling and disabling it accordingly to the enabled var, and then you set the MP enable as enabled, because it will be equal, and in the next check of this thread should run, it will be equal, so it won't be different. Oh my fucking god, this is really confusing. So basically we are checking if the DMP should be off and it's on, or if it should be on and it's off. And to do the logging part in an intelligent way, remember that way of checking and then doing, well, we will check if the enabled, and if it's enabled, we will say it will return the pointer to this string here. Otherwise, it will return the pointer for this string here. And basically, it will show IMU on / off accordingly to the enabled state. Okay, so this is the main part where we enable and disable the MPU. And now we do a pretty dumb thing, which is check if this thread here should run. If should run, and why am I using should run here? I want to execute I will go to the thread class here. I want to execute the should run method inside thread. But the problem with this current setup is that if I execute should run, it will go into a recursive function and will never end. Because imagine, I'm calling should run, calling should run, calling should run. The thing here is that I don't want to call this should run method. I want to call the thread method of should run. So what this does is don't run IMU should run. Should call the original method implemented in thread. So I specify that, and if it shouldn't run, it means by time or enabled. Okay, so if it is enabled and the time has passed, then it will be true, so it will be false because we are inverting. Okay, then we will return false. Okay, so if it shouldn't run the thread for time or for yes, this is Arduino person with no name, lol HTML25. I can read your name. Ha ha ha. Lol. Yes. How about lol? I didn't know live coding supported HTML in the nickname. That's cool to know. Maybe you can do XSS. Continuing. Now it's time that we check for a packet. So let's see if the MPU has data, and if that data can is enough for us to read. Okay. So first thing, we will set the interrupt status as the MPU.getInt status. This means we have a new data coming in, or maybe it's an alarm, like the FIFO has overflown or anything else related. This is in the datasheet, and also get the FIFO count. Get FIFO count. This is inside the MPU 6050. What I said yes, even say yes. Low. What? So going on, the datasheet says that for this DMP we are using, the code, it is a 42 byte long, and basically if the FIFO count is larger than or equal to 42, we should return true, else return false, which is the same as return this. Okay, so it will return 1/0 depending if it's larger than or equal to 42. Okay, and that's the should run method. If it meets the parameter from should run thread and also it has data inside it, it will return true, and then we will receive a call from the IMU run method. Let me copy and paste this code here because it is implementation specifically for 6050. Okay, pasting. Interrupt status and those things are just a way to check if there was a problem or the FIFO overflown. And the important part here is this one here. Okay, so basically we want to get a Quaternion. Remember the Quaternion from the packet we just received. It's all mixed up inside it, and also get the gravity from the Quaternion. Okay, so the gravity is perpendicular to the horizontal plane, I guess, and save that to the gravity inside our drone state. In this case, we are going to stop right here and create a class called drone. Okay, so let's go there and stop right here. So remember where we are here, and create a class drone. This drone class is where we will store the state of our drone. So let's say we have an alarm, maybe a battery is low, or maybe we had problem in initialization or anything else, and even the target that we want to go front, backward, right, left, and those things, we want to save this inside an object. So I will create a class here called drone, and it will only have static properties. Okay, and well, inside the drone we will have the float array, yaw, pitch, and roll. Okay, we also have a static Quaternion called Q, and a static vector float called gravity. And you may be thinking, what the hell is Quaternion vector float? Well, those are implementations inside this helper 3D math class inside the MPU 6050, and you have the class Quaternion, and you have the class vector int 16, and the vector float, and all those stuffs. So we need to include that in our drone file. So let's include it. Helper 3D math.h. And since this is a static method, we need to initialize it. Okay, let's go and create a drone.cpp, include our 3D helper 3D math.h, and include drone.h, and here we will define, not define, but initialize those things. So this is a quaternion, this is a float array, and drone, and drone, and drone. Okay. So I guess this should work. And instead of drone state, we will have to use drone.q and drone.gravity and drone.ypr, and let's switch to everything. Yes, that's it. We have packet, FIFO count, and oh, we are missing the interrupt status. Okay, so we have everything now. This should compile. Let's include the drone. I like to put things in order of size in the includes. That doesn't make difference, the order. And also we need to include IMU. Okay. Now let's see the multiple red lines of errors. Okay, missing here. Missing expecting before drone. Initializer before drone. Oh, maybe this is related to the SQRT. We are not including it in the main file here. So let's include math. Drone Q. Okay. Let's try without it, just the array. Oh, we are missing a double quote here. And error compiling. Why the hell? Was not declared in this scope. That's really weird. Let's include math. That's a bug. Why are you doing this? Next words not declared. Oh, that's obvious. We need to include this here. Yeah, exactly. Good thing I have included it here. Have I done it here? Yes. But maybe oh, it's missing here. That makes sense, but it's still giving problem. Quaternion Q. Let's include what is included here. Okay. No more skirt problem. But we still have problems. Let's try to include this as well. If you have any suggestions, now is the time I try everything. Oh, it's missing here. That makes sense. Should work now. We don't need these anymore. Not this, this. There. So what is happening here? Okay, no more problem. Standard ain't maybe solved it. Okay, we are needing a file named types. And what this file does is simply contain all our types we're dealing with. In this case, I'll include math there as well. If you have any reason why I should include it here, you can say I'm not expert on this. Okay, so let's include this here. I think you should update with F5 autocdu, I'm not sure. Okay then, so instead of helper math, instead of this, types, Okay, so now we include types, and we include here as well. We need to include E2C dev here. E2C dev is used by the wire class, which should be here as well. So we had a problem with multiple includes. Now it's working, almost working. Let's implement this. IMU doesn't name a type. That's because we are not including our own CPP. Fuck. Okay, so this should definitely work now. Drone does not work. Okay, so let's include drone and everything is okay now. Drone. Spectate primary. Okay, so this is a static method we should use. Oi?
Seu concorrente lançou vídeo só vazar o seu.
Como assim?
Mais frente na vaga atrás.
Sério?
Tá fazendo live, vai acontecer.
Você está ao vivo.
I know.
Oh yeah, go, 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 go.
Whoa.
Damn it. Undefined reference, and that means we should uncomment these 3 lines here. Okay. Initialize. How do I initialize the Quaternion? This is not well documented. Oh, I can initialize it empty. It should work. It should definitely work. Oh, Quaternion. Okay. So now it should compile. Yeah! I'm happy now. And we are using only 31% of the memory, which is a good thing for now. Okay then, so let's continue. Drone file is only used to store the state of our drone, so that we don't have to go to the IMU class or anything else. So the IMU updates the drone. Okay. The only thing I don't like here is because that the IMU class is not a static class, and if we have 2 IMUs, they will both update the drone state. But since we are not going to use 2, I will accept that for myself. But the way it should be done is the IMU updates some values inside itself, okay? And that's what it should be done. Anyway, let's continue. And to continue with this, we should now implement the attitude, okay? So the IMU is not being initialized yet. You can see we only initialize the system and the motors. So the IMU shouldn't be initialized here. Since it's hardware, I will initialize it inside the attitude, okay? So let's make it work good. Let's change that. Public. In this case, I will put the quaternion inside the IMU. Okay, the gravity and the YPR, the yaw, pitch and roll. And when the IMU runs, I will only save it to the gravity, to the inside the MPU. I cannot continue with something that I know it's not completely right. So let's hope to compile that. Yeah, it's a hexacopter root killer. So this is working, and we are not anymore updating the drone. Who will do that is the attitude. So let's create the attitude file. And let's go on and save this as attitude.h, and let's do pragma once here, and create a class called attitude, and this class attitude will have a static void init method, and this init method
7-Eleven.
will So I'm going to use IMU, the drone, and the system, I guess. Let's implement the method, which is void. It's inside attitude class called init. And what this init method will do is to initialize the IMU. And I will put this IMU here. The IMU, wait. Let's do different. I was instantiating the MU in the MU file, but that's not good as well. So what I will do is to implement it here. And let's put it as a pointer. And the thing with the pointer is that it will consume less space during initialization, and if we need anything else that requires more memory, the AMU will not consume that until we allocate memory for that. I had problem with a few robots where we required a lot of space in order to initialize, and the solution was to use as a pointer because the space is only inflated after the initialization has used the amount of memory it needs dynamically. So after that we inflate the IMU. Okay, so let's initialize it and instantiate it is equal to a new IMU. Okay, now let's init it and let's see if the initialization was okay. So if the initialization was not okay, let's for now just print IMU not okay and return right away. The IMU is a thread, so let's set the interval to 5 milliseconds. So we will be gathering a sample every 5 milliseconds if available. In the case of the IMU, it will be about 8 to 9 milliseconds, okay? And also, let's create a thread for the attitude. And what this thread will do is to check for new IMU samples and update the drone. And then you may ask, oh, but why are you creating a thread for the attitude just to copy one value from the IMU that we have just read and calculated and update into the drone? Why not put that in the IMU? And there are two answers for that. The first one is that the IMU doesn't know the drone. The IMU only reads the IMU. So that's a module, that's something that shouldn't be touching anything else than the I2C port, okay? Attitude is something that links both of them. It will gather the sensor data, transform into the orientation and attitude of the drone, and save that. But since our MPU, the 6050, is already doing the computation to merge the gyroscope and the accelerometer data, and transforming that into a single quaternion, okay, that quaternion is the final result that we wanted to achieve in the attitude. So the attitude is only going to copy that because it's already done by the MPU, okay? But let's suppose in another case you had an MPU that is not the 6050 and you had, I don't know, an accelerometer and a gyroscope and you wanted to merge those values, okay? This thread here is the one who would get that data and join and fusion them and output the attitude, okay? So attitude must make sure that the orientation of the drone is correct with respect for the ground, okay, so for the gravity. So it gets the data, either it is raw or it's filtered, and make sure that the state of the drone is updated, okay? So let's get this thread attitude and initialize it. Attitude thread, in this case, let's set the interval to 5 to be linked with the IMU, and thread at thread, I set it to TED thread. Okay. So let's make this method here and fast forward the declaration of the method so that it exists in this state even though it's implemented after. Forward declarate all X. So on run the thread attitude callback. Okay, so now we add it to the system, and one thing that is good to do is to add the thread attitude after the IMU, because imagine if the IMU runs after the thread attitude, there may be no data. Oh my god. Caraca, quase fechou a porta e fudeu com um cabo de rede.
Sério?
Isso também fode. Okay, we are safe. The Ethernet cable almost was destroyed by the door, but we are safe now.
Yeah.
So if we run the IMU before, the sample will only the sample will be fresh when the thread attitude runs. But if we invert that, then there may not be ready for reading, and we may get a delay of 5 milliseconds for a simple thing. So let's add to the system in that order. You notice that I don't put the E here because it's a pointer, but here we add thread attitude, and that should be okay. And what do we do inside the thread attitude? Well, we need to get that data from the IMU and copy it to the drone. Okay, so the IMU here, let's go to the drone. Q is equal to IMU Q. We actually only need the YPR. Okay, so let's only copy that. 0 is equal to IMU YPR 0 and copy that to 1 and 2. Okay, so we are copying the YPR values, and let's make a new thread here just for debug. And this thread used in debugging. Debug thread. Set interval of 500 milliseconds, maybe 400, a little bit faster. And on run, let's call thread debug callback, and we need to create that callback here, and we need to create the method here, and in this method we will only log what the drone has. Okay, so let's add this thread debug here in that order. There is something else we need to do here, but it's not necessary. Okay, in here you could check if the IMU has new sample, and you only copy that if there is a new sample. But since the data, changing the data to the same data is not inefficient. It's just a few microseconds. We will be copying it anyway. Okay, so let's log YPR space log the drone YPR 0, which means the Y, and then log I space. Let's put a tab and then line break. Okay, so we have now the YPR. If this compiles it should work, but it doesn't compile. Okay, so why it doesn't compile? Because in attitude we are not including attitude. That's inception. So let's download it to the drone. Problem uploading. Upload. And eat something. Okay, I guess it's working. I'll turn off and on. Okay, we receive pingback, but things are not working, and that's obviously because attitude init is not being called. Okay, we do everything and we forget the most important thing. That's humans. Damn humans. Okay. Attitude has not been declared because we have not included. Okay, includes are hell. Uploading, and it's really uploading. So hope it works. Switch the cam here. Same one. Okay, it's uploaded. Now let's see the serial port. And we are getting the yaw, pitch and roll. That's awesome. But there is something you should notice. The values are really low. And that's because they are in radians. Okay? When we have something in radians, to convert to degrees just to show us, we should probably multiply. Let's save to the drone the converted value, okay? So let's multiply by 180 divided by half p. That's by p, sorry. So multiplying by this will give us the real value. Let's compile it and download. That's pretty big now. Okay, so shut down and shut on. And now we have something that seems to be okay, but it's not. It should be working. Let's turn off. Let's turn on. Okay, so there is a problem here. It seems that only one value is getting saved. And that shouldn't be happening. Why is this happening? Run. The values are different. I can ping. I can turn motor on, off. Unless, of course, so let's print it here. Got data, so that we make sure data is getting saved. Okay, data is being received. We are saving it. So the problem is not here. Let's go to the attitude. Check for new data. That's something we can check for this new data flag. Okay, if IMU new data, let's log new data, and let's set new data to false, so that we know it hasn't any more new data. Debugging is so boring. Okay, uploaded, resetting. Serial is not working. So we have new data. And it seems to be working now, magically. I don't know why, but it's working. That's what matters. Okay. Yay. So 0 degrees. the yaw, as you can see, the yaw is changing to positive value. The first value, right now it's 70, and here is the 0. It is not good. I don't know why it's shifting. This MPU is really good. Let's reset it. Okay, this is pretty unstable. And my serial port is even more unstable. Oh. It may has to do with the capacitor here, which is disconnected, and it's needed. That's pretty weird. Okay, restart. There is something wrong here. And I know what it is wrong. We are not enabling the DMP, I guess. This part here, it should be printing something, but it's not. It is not. How can it be? If the IMU is not initializing correctly, it should be a problem, but I think covered it here. And also here. Unless, of course, we are not calling init on the attitude. But yes, we are calling init. So that's not the problem. Let's simplify that. We are debugging inside EMU. It should run. Should run. Is it being called? Because if it's not, it will be a problem. Enabled, it's true. MP enabled is false. It should be different. Unless, of course, we change that here. Well, what I'm looking at right now is some sort of bug, because we have implemented the automatically turn on and off of the MPU here, and it should be logging something, right? But it's not, so that's the problem. In order to know that we are initializing the MPU, we have placed this log here, and it happens. Let's see it again. Turning on now. If my serial port was okay, you would see it. Let's reset it. Let's turn off. Let's open the serial port. Go serial port and turn on. Okay, so EMU thread. Okay, it's working now. What the fuck? So it's perfect now. Ok, it's working. E aí, Gabriel?
Bem?
Beleza.
Cara, os projetos aí.
Estou live. Well, let's leave it still. This IMU is not in a good state, I guess. Okay, it's stabilized. It's a little shaky here. That's the reason why the pitch is not so correct. So look at this so that you can understand. The pitch here is caused by this little fluctuation. We put some hot glue, but since we are removing and putting in place, that may happen. So that's the reason why we have this differentiated value on the pitch, which is the second value you are reading. But that seems really stable. Let's rotate around the yaw X. Okay, let's zero it. So 0 is here. Let's rotate 90 degrees, and that's almost, yeah, it's perfect. Let's go back and rotate 90 degrees to the front. Okay, pitch is 90 degrees to the front. And this is where deadlock happens. As you can see, the yaw is crazy. The yaw increases a lot. The roll now. And it's okay. As much as it gets to 90 degrees, we get a gimbal lock. So this is okay for now. Remember that what we are reading here is a sample every 400 milliseconds. It's not every sample, just not to flood the serial. We could change this, but you know, it's just for debugging, okay? Good thing about using thread is that if we comment the line where we add it, or even disable it, we can remove that. So let's do something in the system, which is when we receive the command I from IMU, we will go to the IMU and set the enabled as the opposite of what is currently saved there. So we will toggle the enabled value. And let's log this. Debug menu. Okay. The problem here is that the IMU is not publicly available. Remember, it's not here. It's not instantiated in this IMU. It is instantiated in the attitude. So what we have to do is put the extern inside the attitude. So now our MU is open for all the other files, and we can access it in the system. So let's test it out, but let's begin with it disabled. Wait, I'm doing something wrong here. Wait. Okay, I have done something wrong. It's not the IMU thread that I want to be publicly open. It's the thread debug, and the thread debug is not a pointer. So in the system we don't need this. We can use this. Okay, this should work now, but EMU is not EMU. It's thread debug. Okay. So basically we have done a simple on and off for the current debug we are having, okay, using the thread system. Thread debug was not declared, okay. Thread debug was not declared because we didn't include attitude. But if we include attitude, thread debug is declared. So you are dumb C++. Thread debug was not included. Okay, IMU is on. Let's test the debug. Debug is on. Debug is off. Debug is on. Debug is off. The only thing I would change so that we can continue is change the interval of the debug because it's not so smooth. Let's put 200 milliseconds. And that part is completely done right now. Okay, so we are updating the drone data, the state of the drone, and we are doing some debugging depending on the state of the thread. Let's close a few files here. Let's close attitude. And this is a good moment for questions if you have any. And a good moment so that I can drink something because my throat is really thirsty. So, questions? And if you have any suggestion or anything you would like me to cover, we have not done it yet, you know that, but it's good to know so that I can include that in my class today. So let's create a new document and put questions. 5 minutes. Okay. So 5-minute pause. So let's go back to our craziness with drones. Well, since no one has any questions, any suggestions, you may be sleeping, I guess. It may be boring, I guess, as well. But let's go on. Here is our code. The whole code for now. We are initializing the system. We are initializing the motors and the attitude. And something that we need to introduce now are alarms. Well, you can think in an alarm as something that went wrong. So let's suppose that you are flying a drone and the drone is upside down now. That's wrong. It shouldn't be upside down. Unless you are really fucking crazy at driving drones, it should never go upside down. And that's something you should prevent. And if that happens, the first thing you should do is stop the motors. Okay? Other thing that should stop the motors. Let's see. Well, you initialized the drone and something went wrong, like the IMU or anything else. You should never turn on the motor if the initialization was wrong, right? So that's another alarm. Other kind of alarm is the low battery alarm. So imagine the drone with a really low battery that will damage the battery, because lipo battery cannot be charged if a certain point in voltage is the drop in voltage is really high, and that's a problem. So those are the three main alarms I can think about. So let's implement that, and the best way, the best place in fact to implement alarms are in the drone class. So remember the drone class that had only a few methods, a few properties? Well, let's implement it here, okay? Drone is something that we could probably initialize, okay? So let's make an initializer for drone so that we can initialize the state and everything else. And let's create a new enumeration, okay? And this enumeration won't be declared here in drone. Let's declare it in the types. That's what types is meant for declaring new types or anything else that is global to the program, okay? You don't declare classes here, only utility types. So in this case, alarm, it's a type, okay? And it's an enumeration, and the values it can assume is none. It can assume, and let's say none is 0. It can assume alarm low battery, alarm, it can assume alarm low battery, and it can assume alarm crash. Okay, and it can assume alarm in each which is some problem caused in the initialization. But in fact, our alarm can be declared as the state of our drone. So imagine that your drone has a state, and a possible state is the alarmed state. So let's change it to state, okay? And the state can be initializing, sorry, can be known, not known. Let's think in a neutral. Oh, neutral, not neutral. Stop it. And it can be stopped, and it can be armed. Okay. When you have an armed drone, it doesn't mean it has a gun. It just means it is the motors are armed and the drone is stabilizing itself. Okay. So basically, when you turn on the drone, the state it initializes is they stop it, okay? And if you command it to fly, then it will go armed. And if you crash it, it will go crash it, and or maybe low battery and all those other states. So this unknown is actually not a variable yet, but we will create that variable inside the drone, okay? And here is the state and state. So let's declare the state with the name state. That's redundancy and I like it. Inside drone.cpp, let's initialize the state. State, and we need types. Okay, types are already there. Drone state equal to stop it. Okay, that makes sense. Now let's implement the drone. Void drone init, and here is where we set the initial state. We have already done that. So let's see if I can do it in the init. No, it's better to do here. You guarantee it before init. And in init, let's have something else here. We don't need initialization here. Let's remove. Okay. So we are initting, and now let's create a method called setState. Oh, shake. Yeah, this board is self-made. It's a single phase Arduino powered controller for drones. It uses an MPU 6050, and it also has an ESP module here so that we can communicate with it. And those sockets, they are meant to be plugged in the drone here. So you plug each motor here and it tries to fly. And that's what we are trying to do here. Okay. There is also oh, this project will be on GitHub, so if you want you can access it, but it's not right now. So that's it. Okay, so set state is where all things that sets the state of the drone will call. We won't never change the state directly, because when you change the state directly, something bad can happen. For example, if you set the state directly, you may not be able to stop the motors instantly when an alarm occurs. Okay. So void set state, and we will pass in the new state. Okay, so this new state here, let's implement that method. Let's save it, but before saving, let's check if the new state no, let's not check for that. Let's think before checking. I want to check a state. Actually, check, this is a really simple board that anyone can build at home. So the project, the open source project, is so that anyone can build a custom drone with some time, you know. And this here is 3D printed, so yeah, we can pretty much build it on any house today. And this can also be cut in MDF or something like that, but we haven't tested it yet. So it's a cheap drone, it flies, but the question you ask is it's cause of weight, and so it fits better with your drone. Yeah, we made it from the ground, so it's actually made to fit with everything. Continuing, the set state should set the state and check if it's an alarm. The alarm state is anything other than stopped and other than armed. So what we want to check here is if the state is different than armed. Like the burn and think about getting to don't put in that. Yeah, an 80 mega would do the job, and it's doing the job. Here is the 80 mega 328 running at 8 megahertz, and that's pretty much an Arduino. Okay, it's running the bootloader with the Arduino. It's the bootloader from Arduino. So if the state is not armed, which means it's not something we if it's not armed state, it means we should stop the motors, right? So let's stop the motors. Basically that. Let's set the state before and check for the changed state more guaranteed. What else? Here, set state, stop motors. Okay, so there is something else we should be doing on the motor part, but that's fine. And set state. When you set the state, let's check before setting the state if our state is different from the new state, and if so, let's log it. Changing state, and we log the state, the new state of our drone. Let's break that line. Okay, so this is just for debugging. State equals state, and if not, stop the motor, and that's fine. So let's now set the state to armed and set the state to stop it from the command line. Okay, so here, instead of setting motor power, let's set the state of the drone to armed. We are going to need types, and we are going to need drone. Yeah, I guess it will be finished today. The problem we have is with the battery. The battery we've bought from China is a cheap one and doesn't even handle one motor. Each motor consumes 1 amp, and this is a shitty battery, and we are really pissed off with it because we don't have any other. But we may try with a 2S battery using only one side of it, but I'm not sure if it's going to fly today. So if it's 0, let's set the state to stop it. Okay. Armed state, stopped state, and then in the armed state we will do the control part. That's fine. Let's see if it works for now. Just be sure that everything is okay. Multiple definitions of a known state. That's true because we didn't put a pragma once here. So it's including multiple times. It should be not defined multiple times now. State is equal to new state. State was not declared in this. Of course it wasn't because I didn't use the correct syntax. And where is the drone? Here. Void drone state. Now it's correct. There was a bug here. And let's see if it works now. Okay, set state. Cannot declare member function static. Okay, in declaration we don't use the static field. Let's try to build it again. Log was not declared. Of course it wasn't because we didn't include the configs. Now everything should be declared. Not yet. Serial was not declared in this scope. Whoa. That's new. We did it so well until now. So basically it means please include Arduino. Okay, so it's initialized. Let's send a 1. Pingback is being received. But I guess, oh, we had a problem here. Motors is not included in drone. I like to include only the necessary so that we don't include unnecessary things and we keep control of what is being used by what. Okay, not drone, motors. And you should be here. Set state not a member of motors. Of course it's not a member of motors. Where I was with my mind. It's not. It's drone. Drone. I guess it will work now. Yeah, it's working and it's not uploading. So disconnect, connect, and upload. Okay, so EMU is on. Let's debug the IMU, it's working. Okay, and let's, okay, state is 1, 0 should stop, state 0. And that's pretty much the state control of our drone. Now the next part, let's go back to our schedule. We have done the motor part, we have done the IMU part, we have done the attitude part, we have done the controller. No, we haven't done the controller, neither the commander. And that's where the magic starts to happen. So let's do the stabilizer. The controller is more it's not a module, but we will implement here is the PID. Okay, and the commander will be the last thing. Something that we need to do here as well, and we have it done, is the system global root drag controller, and it's okay, but it's missing something important, which is the battery voltage reader. So let's implement the battery voltage reader and checker. Okay. To do that, a good place to put it is in the system. The system is more hardware part, and it takes care of maintaining the system working, so anything related to that we should place it here. So let's create a new thread that we call, let's call it battery checker, and we will have a battery checker callback. And let's implement that battery checker callback here, and let's set up the battery checker here. Say battery checker dot set interval. I want it to run every, I don't know, 3 seconds, 5 seconds, 4 seconds. Yeah, good number. And when it runs, I want it to call the callback. And let's add this checker as well. Well, now that we have a battery checker, we should know that the basic workflow for this is battery really low? Yes, set state to alarm low battery. And actually, is this battery really low? Set the state to low battery. Else if battery is kind of low, set beeping state to beep. But in this drone here, we don't have any space for a beeper. Okay, so what we will do is to change the speed of the LED. So when the battery is low, it won't flash like this, it will flash like only flash a bit and then keep off, like an advice, okay? So it's like flash and stop, flash and stop, flash and stop, or maybe we can go faster a bit with the LED. Anything can be done. And otherwise, it will set beeping or flashing state to none. Okay, so if the battery drops too low and then go up again, you should stop flashing none. And basically that's it. So what we do now here is translate this to C++. Uma bateria de V944 é bom?
V944? Pode ser que seja.
É daqueles helicópteros?
Pode ser, eu acho que o 944 é um helicóptero meio grande, não sei. Pode ser que seja.
Okay, we may get the battery to test the drone. That's so happy. Okay, so if the tension of the battery is less than battery critical, we should do something. As if the voltage of the battery is less than battery warning, do something. Otherwise, clear. The bat critical and the bat warning is not defined yet, so let's define it here. I would put it on the top because it's more hardware stuff. So battery. Let's define the battery. João,
Oi?
essa aqui, ó.
Hello?
500 mAh.
Da FUC.
Será? 30C.
That's right.
Se pá, rola.
Let's try.
Podemos pegar lá pra tentar. O que você acha?
Let's see.
Ele mora aqui perto, eu acho. Okay, so we may find a battery so that we can test with the motors. Verdade. Anyway, going on. Here we have the battery warning, which is about... João, qual é o limite da bateria?
3.5.
E o limite de warning?
Não, o fact é 3.3 da bateria.
A gente põe 3.5, né?
A gente põe 3.5.
Tá. E o pra dar warning?
3.5.
E o critical?
The motor critical 3.5 e o warning é 3.6.
3.6, okay. So the warning will be at 3.6 volts.
3.4 é
And the fine battery critical will be at 3.4. So that's it. Você já tem o... Vocês tinham feito, não foi o mapping?
Tá lá.
Aonde?
No outro já tá.
Já tá aqui.
I think so.
Ok. One minute. Não tá implementado. É o mesmo do robô.
Não, porque isso tem que pegar a diferença, né? Tem que pegar a diferença entre... Não, a gente alimenta ele com 4.2 e joga no analógico 3v3. Ele pega a diferença entre o 4.2 e a referência do analógico. Eu vou pegar aqui então. Foi o...
Vocês fizeram no seu computador, foi?
Foi.
Tá, viu lá. Okay, so we have spent some time mapping the voltage to the analog read of the drone. João can explain a bit how it works. It's really simple to read the battery of the drone. So I will pass on to him. Let me just start the Altium Designer so that you can see the schematics.
But the schematic is pretty straightforward. It's just like we have an Arduino that's being part of the battery, but we have to measure this battery while the Arduino is running. We could have done something like, couldn't in fact, like a voltage divider, because we do not have an analog reference. It's like if we did a voltage divider, the voltage that is feeding the Arduino would be the same. You would have the same drop of the voltage read by the voltage divider. So that was the problem. We fixed that by putting the voltage on the Arduino. We feed the Arduino from the battery, from the VCC in the battery, and we put like our IMU has a voltage regulator, like right here, that regulates to 3.3 volts, and put we put these 3.3 volts in an analog part of the Arduino. So if the Arduino is being fed at 4.2 volts, the 3.3 in the analog will give us a value of like 700 or 600, something like that, and then we can read. If the voltage drops to 4.1, the analog will like grow. Then we can know this difference by storing these values and know if the battery is lower than before or something like that. That's what is in the system.
Okay, so I'll show you the schematics here to be clear.
Yeah.
And then we continue.
Don't mind the 0 ohm resistors that the board has, because to do it like single layer and keep it, like I said in the beginning, DIY, we made it a few adjustments on the board, like to adding some jumpers and some stuff to really make it easier for someone to make at home and things like that. Now Ivan is killing his computer by running a stream and a virtual machine running Windows, running Altium Designer, but it's okay.
Nossa, tá muito lento.
Yeah, his computer is like trying to do something, but it can't.
Oh my god.
And as we could see, his Windows is not documented, right? Not activated.
But it's original. It's
But
because
original.
my old computer broke without unregistering. And this one thing I am cloning the license.
Now we are in the autumn zone.
I need a mouse.
Não, esse vira na esquina, olha esse acha.
Nem tá vendo.
Faz público.
Oops, Google Drive. Okay. So this is the schematics that Joan has just explained. And the part where we check for the battery, it's a really simple part, and it is where is it? ADC 0. ADC 0. Okay, here it is. So we basically get the 3v3 regulated from the MPO. We put a 1K resistor in series and we read that value. Okay, so what we know is that the value from the analog in is 3.3 volts, but the voltage that is powering the MCU is varying. So in fact what we are reading is the VCC from the MCU, not the voltage from the analog in. But the thing is, when you supply a voltage in the VCC, the analog reference used is the same as the VCC, which means that if we are supplying 4 volts to the VCC and we supply 4 volts in the input, that will lead us to 4 volts for a full range of full value from the analog input, which means 1023. Okay, but since the VCC is a bit larger than the 3.3 volts, because the 3.3 is regulated from the VCC, the value from the ADC will be less than the maximum value and will continue to grow until arrives at 3.3 volts and they both are equal or really close to each other. So that's the idea. Drive. Okay then, so we open it just to show you that. Let me close everything now and reduce my CPU
usage.
cadê? Not here.
Yes, he's open plan.
No, not VDDC.
Okay, so this is the part where we convert the ADC to a real voltage value. This is a sketch made by João and Vitor, and read battery is what we want. Channel, analog read channel, and this is the method we want. Okay, so let's copy that. Let's copy that and define the battery to voltage directive that will basically convert what we want. So wait there, I have a project here that I have implemented this Google Drive. So here is it. I'll use it as a variable. Okay. So this should work. And battery voltage is the snippet of code that we use to check the battery. Something that we should do is to store the battery voltage inside the drone state. So let's put a float vbat, which is the value of the battery right now. In battery checker, we will go and change the drone vbat to the value of bat to voltage, and it will run this snippet of code here, and this code will convert the ADC to something real. Okay, bat to voltage, analog read, ping v bat. Damn it, I don't know the ping v bat, and that's bad. Oh. João, você lembra o pino que tá tensão na bateria? É, eu não vi não. Se eu for. Ah, zero? Okay. So it's on A0. And here we read the ping vbat. Okay. And instead of checking vbat directly, we read from drone. And if vbat is less than battery running, okay. If it's critically low, one thing that we may want to do is to filter it. So let's create a new filter here. Criticals, which starts with 0. And if critical plus plus is the same as checking if critical is larger than 3 in this case. Let's put it 3. And if so, we will set the alarm, okay? But I don't want to do that in another if, so let's just do if the battery is critical and criticals plus plus, which means some criticals to 1, sorry, if criticals is larger than 3, wait, this won't work because we need to sum it only inside. So yeah, we need 2 ifs inside the other. So criticals, let's sum 1 to criticals and check if it is larger or equal than 3. And if so, we set the drone state to alarm low battery. That's okay. But if the drone VBAT is less than the warning, we should blink the LED faster, okay? So we won't do this here. We can do it on the heartbeat, right? So in the heartbeat, where we blink the LED, this is blinking it, we will change the heartbeat speed, the interval, okay? So the interval will be basically like this. If drone VBAT is less than or equal VBAT warn, no, not warn, what's the name, bat warn, yeah, warn, is it okay, bat warning and critical, bat warning, so it's a warning, we should set the interval to, let's say, 100 milliseconds, okay? Else if, or even only else, we set the heartbeat to the usual one, which is the value of 500 milliseconds. And we want to check before that if the drone is in the alarmed state, okay? So the alarmed state must be different. The alarmed state is like I am stopped and I cannot do anything. So let's put drone state different than stopped and actually drone state, let's check if it's armed, okay, and if so, let's set a different state in the LED, and let's also check if the drone is different than stopped, which means it is alarmed. Okay, but then there will be a problem of priority, because if the drone is armed and the battery is dropping, then that would still be the state of armed. So the priority here is to check for the battery low first. And now we have our priority okay. So if it's armed, drone is flying, so let's set the interval to 100. No, that cannot be done. Let's set to 250. So it will blink twice as fast. And now we will do something really cool. We will make the LED blink without having the same amount of time on and off. So imagine that it will flash really fast and then keep off. So that's the idea here. The heartbeat will be like that. So I want it to save the state on a Boolean flag. And let's invert that state and set it to the LED ping. So every time it arrives at this function, it will invert the LED state and then set the state to the LED. And the next call to the function, to this method, will be only 500 milliseconds in the usual, okay? But we want it to be 500 milliseconds if the LED state is on, okay? I'm sorry, off. So if the LED state is low or false, or even if the LED state is true, then we may say, is LED state true? Yes, which means the LED is on. So I wanted to call this function again after 550 milliseconds. Otherwise, you will call it 500 milliseconds later. And this will cause the thread to call it 50 milliseconds later, and then 500, and then 50, and then 500. And it will go switching between them based on the state of the LED, which is changing every time it runs, okay? So this is a way of changing the way the LED blinks without using delay. So if the drone state is not stopped, it is alarmed, and I want it to set the state. I want it to be on most of the time and off only 100 milliseconds. So you see the LED blinking like this, and that's alarm, okay? And if the drone is armed, you will see a blinking LED of 250 milliseconds, okay? Blinking twice a second. And if the battery is really low, I want to do no, let's keep it 100, which is twice as fast as the usual. Or we can even do the opposite as the alarm. We can set it like this, so the LED will be 100 milliseconds on and 900 off. I guess that's all we want to do. And let's see if everything works now. Criticals. Okay, our filter. And here, oh, it misses. If the drone is not in critical mode, what we want to do is to check if the drone state is alarm low battery, and if so, we want to reset the state of the drone to the stopped state. So set state to, we can put a else if here instead. Set state to stopped. So this is basically the battery went low but then went back to OK. So we won't do anything. And one important thing here to do is to reset criticals. Otherwise, criticals will always be larger than 3 if you went to battery critical once. Battery critical, why I do this? Because when you start flying, the battery voltage drops a bit, and that's bad. And if you go into critical mode and then you want recover from that, you have to turn off and turn on your drone, and that's not an intelligent thing. Okay then, so let's try to upload this. Unfortunately, we don't have a buzzer here. Would be really nice to beep some stuffs. Okay, we didn't initialize the drone battery state. Drone to 0, and let's add something else to our debugging. Let's put a else if command is equal to v, and let's print the voltage. 30 log drone vbat and log /n. Okay, and that's our debugging the battery so that we can read the value. Hope it compiles. Okay. Uploading. That seems okay. Let's read the voltage. 4.2. That's weird. I don't know in which state it is, but the voltage, as you can see, is 4.27, and what the external source is reading is 4.3. So let's go a bit and drop that to 4.1 and read. Okay, it's pretty stable. Let's read 4. Okay, 3.8. Okay, it's pretty perfect. 3.7. That's awesome. 3.6. 3.4. And that's when our alarm should be warned in about 12 seconds. It should alarm. Okay, so as you can see, the state changed to 4, and 4 is the state of low battery. If we go here, this is 0, 1, 2, 3, 4. 4 is low battery. So we are in low battery mode, and it's alarmed. And as you can see, the LED is blinking in the alarmed state. Now let's make sure it's working. Where is system? System is not here anymore. Okay then. So not in system. Yeah, it's in system. So let's go back to normal and see if the battery, if the alarms reset it. Okay, the alarm is 0 now, so we are okay. Now let's go into armed mode, which is 1, drop to 3.3. It should change to state 4 in a few seconds because of our filter. Okay, it's in state 4. Now let's go back, and it shouldn't go to armed state. It should go to state 0. Okay, it's working. So in case the battery drops and then drops back and then comes back, the drone won't start flying again like a craziness. This part is pretty much done. Only the LED part, I think it's not perfect yet. Let's put the idle state with a large blinking. I don't want it to be mistaken with the low battery. And that's the only thing I would do for now. Let's see if the LED changes to 2 blinks per second. Okay, that's pretty slow. Let's put 100. I like blinkings. And okay, no more blinking changes. This is kind of useless, but it's important to you to know the state of your drone. This is using a single LED to show multiple states, but of course you could put a buzzer. That's what I do in my robots. And I separate the alarms, which is toggled from the LED, to the battery alarm warning, which is in the buzzer. So both things can work separately, and that's the idea. The last alarm we should take care is the inclination alarm. But that alarm shouldn't be in the system, I guess. The inclination alarm should be in the attitude or in the controller. I would put it on the controller or in the stabilizer. So let's put it on the stabilizer and start the almost last part of this firmware. Okay, so stabilizer is who makes sure to not make the drone explode or fall. Also does what the commander wants to do. And let's add something here. Make sure drone stops flying when it explodes/fall. So that's our fallback. Oops. Let's create the stabilizer. And stabilizer.cpp. Let's include both config and types.h. Let's include thread and let's include stabilizer, the drone, the system, and for now it's this. The stabilizer will be a class as well. and we will have a public method which is static, doesn't return anything, called init. And this method here will be implemented. And what this stabilizer will do is to initialize the threads and also the motor output thread. So we will divide it in 3 parts, I guess. The first thread is the thread called thread check fall. This thread here will be run every 550 milliseconds, and when it runs, it will run the callback that I will create now and forward declare it here. So let's implement this here. And what this does is to check the pitch and roll and see if it's greater than 45 degrees or maybe 70 degrees, I don't know. Let's test it. Okay, thread fallback, safety thread. We also have a thread called stabilizer, which will do the computation of the PID and output to the motor. And I would divide it into the motor output and the computation of the PIDs, but we can do that in the same thread. We don't want it to be over complicated. So let's initialize. And the stabilizer, I want it to run every, I don't know, 10 milliseconds. Maybe 5, maybe 7. It's good to be synced with the IMU data. So if you're getting data, I don't know, 10 times per second, you should do that computation every time you read. Or if you're reading you are integrating something like reading gyroscope and integrating, you should do the attitude computation about 10 times faster than your actual control. I will set it to 10, but we can set anything between 5 to 10 here. I will be using 10 so that we can have lots of time to work on other things like checking battery and etc. So stabilizer on run, execute stabilizer callback, and this callback here, we will define it here. And the last thing we have to do is to add threads to system. So system, we have included it, yeah. System.add, and I want to add the thread check fall and the thread stabilizer. That's fine. The thread check fall is the implementation. It's really simple. Okay, and basically what we have to do is check if the drone state is armed. So we will only check for fall if the drone state is armed. I don't like to put a if in the code and englobe everything. I prefer to do the inverse. So if the drone state is different than armed, just don't continue. Return right away and don't continue to execute the function. Okay, this is more cleaner because you don't have to. If you have another if, you don't have to put it inside another if, and it's much easier to understand. If the drone state is not armored, skip it, okay? So basically, now that we have checked the state, let's see how to check if the drone has fallen. Well, we can do that in two ways. If we go to the IMU, we will see that we are getting three things from the IMU. The Quaternion, which is the orientation, the real orientation. The gravity, which is the direction of the gravity, okay? And the yaw, pitch, and roll. The gravity has three components. It has a Z, a X, and a Y. And the gravity, the component of the gravity in the Z-axis is basically how big it is in that axis. So if the gravity in the Z-axis is not big enough, it means that we have tilted or rotated a bunch of degrees, you know, so we are not in a stable position. So in order to use this here, we will have to read the gravity, but we are not copying the gravity to the drone state in the attitude. So let's do that now. The drone has new data, yes, let's copy the gravity, and here we copy the yaw, pitch, roll. So let's go there and copy drone gravity is equal to IMU gravity, and in here we shall get the state of the gravity. Okay, this should be updated, and the gravity state we will have to debug right now. So let's set the interval instead of 50 to 200 so that we can log that. Let's log the drone gravity dot z, the zx. Double quote, please. So let's log all of them so that you can see it in action. X, Y, and Z. And here is tab, tab, and tab. Okay. So try to fall back. Oops, here we have the same name for both of them. Stabilizer is empty for now. We added to the system, so everything should be fine unless we have a compiling error, which we always have. News. Missing this. I hate this. Okay, only a small problem. That's fine. Out of sync. Compile again. Uploading, and it's really uploading.
Você tem 7 horas, cara. Você tem 7 horas e 10 minutos, velho.
O que é?
Isso.
Sério? Eita.
Cara, não sabia nada assim, então vai estar no top do Live Code.
Okay, so that's arm. It's armed, and we are not debugging. Why not? It should be debugging different than armed. Thread, check, fallback. Yeah. Oh, of course. We are not running the init on the initializer. So let's put it in the main file here. Put it after the attitude. And look. I hope it works now. Stabilizer is not defined. Now it is defined. Oh, failed to upload. Uploaded. IMU is on. Let's arm. Okay, that's gravity. As you can see, the X component of the gravity is 0, the Y is 0, and the Z is 1. So imagine this as a 3D vector, okay? It will never go beyond 1 in this case if you sum every one. Let's, if you sum and take the square cubic square, not cubic, the root, yeah. So square root, yeah. So if you see, when we inclinate, the z-axis, which is the third column here, goes really small. And if we are upside down, which is something bad, it will go negatively to a maximum of -1. So it goes from 1 when you are upside, when you are fully upright, and even if we shake it, okay, the FTDI have dropped, but let's go back. Okay, so even if you, damn it, be tolerant, I guess. Okay, so we are back. Even if I shake, damn it, let's restart. Even if I shake, oh, I'm not reading material here. Oh, that's bad. Turn off, turn on. IMU hasn't initialized. And restart. Esse seria o monitor. Ele tá uma bosta. Ele não... inicia. Na hora certa. Ok.
Tira e coloca o USB. Tira e coloca
Okay,
o
ping
USB.
is back. What?
Você só tipo rodou ele e deu bosta?
O FTDI saiu.
Tira lá da ponta. Fecha o monitor. Muito bem.
Initialize it. Okay, it's working now magically. I don't know why it was wrong, but anyway, let's arm. And as you can see, let's try not to disconnect here.
Value the same.
The gravity doesn't. Okay, we have a problem. Zero. We have a problem. É o capacitor, cara. Deixa eu tirar o capacitor.
Não precisa estar soldado?
Você acha que precisa da soldada?
Não, mas ele tá dando mau contato, eu acho.
Não faz o power cycle completo.
Tá, desliga lá. Ok. Arma. Você solda. Espera aí. Desliga. Não liga. Liga. É isso mesmo. Okay. So this is the gravity. If I shake it, as you can see, it doesn't change it a lot. So that's it. So let's see an angle here. If the gravity is, I don't know, like this, it is probably going to fall, which is about half, 0.5, 45 degrees. Okay. So if it's below that value, we will stop the drone. Okay. And let's define that here. Stability check. Stay define ability z gravity z mean, which is 0.5. That's a big name for a definition, but okay. And in the stabilize, let's check if drone gravity x is, if it's okay, right? So if it's greater than stability gravity z mean. If so, return. And if not, it will set the state of the drone. State alarm crash? I don't remember. Crash it. Okay. So here we set the state to crash it, and this is where the alarm will be set, and it will automatically stop the motor, because inside the drone set state, if the state is not armed, the motor will stop automatically. Okay, so that's it. We can test it. Gravity is not defined. Gravity is. Okay then, if we inclinate it, doesn't happen anything. But if it's armed, if we inclinate it a lot, then the state change to 3, which is it fall, so crash it. But if we reset it and go on, we can change to state 3 again. And it's really fast, as you can see. Let's reset it. So it's working. That's okay for all sides. And even if we started with lots of inclination, it automatically changed to 3 really fast. So we don't have any problem with safety for this drone right now. Now let's move on to the PID part and the stabilizer part. So let's just document a bit here. Checks if drone has inclinated too much. And the stabilizer thread will basically do one thing first, which is check if the drone state is different from armed. If it is different than armed, it will always try to stop the motors. So we need to include motors here as well. And this is because, and now we return, this is because we don't want it in no way to keep the motors on unless it is armed, truly armed, okay? So it won't get to any line other here if the drone is not armed. That's basically it. And to begin with, we already have the orientation, and we have anything else here. We have everything we need. We don't need to mind anything else because we already checked for the inclination, we already checked for the battery, we already checked for everything, we initialize everything. So now it's time to take care of keeping the drone flying. Okay, so in theory, the the part, not the part, but how we make sure the drone is stable is by using 3 different PIDs in each axis. Okay, I explained this in the beginning of this video, but I will explain again. All right. So imagine that the drone has 3 main axes. The Z-axis. Let me change the camera here so that it is bigger. Not this camera, not this camera, not this camera, this camera here. Okay, so imagine that we have this axis here, which is the Z-axis, and if you rotate the drone in that axis, it is rotating in the Z-axis right now, and we call that the yaw. The yaw is when the drone rotates around itself in the Z-axis. Alright? So the yaw is positive to the right and negative to the left. Alright? This red painted here area indicates the front of the drone. So the pen is right now pointing to the front of the drone. And when you rotate along that axis, you are doing a roll. Okay, so this is the roll. And the roll is when you rotate along this axis. And the last axis is this one. It is perpendicular to the roll and perpendicular to the yaw. And it's called the pitch. The pitch is this movement here. And the pitch is also an axis that the drone can rotate. So how does the drone rotate along the pitch axis using the motors? So you can imagine that if the axis is here, we increase power on the back and decrease power on the front. So this makes the drone inclinate to the front and go forward. Alright? So this is the pitch. The pitch makes it go forward and backward. Alright? If you give more power to the front, it will happen the opposite. And if you go along the y-axis here, we have the roll, and to do that you can increase the power of these 2 motors and decrease the power of these 2 motors here. And this will make the drone go right and left. Alright? That's the main idea. And the last one is the yaw. And the yaw is really, it's kind of different from the other movements, because to be able to move in the yaw directions, you must use a really cool property of the rotating propellers. When the propeller is rotating, what happens here? Imagine that the propeller is rotating and that I'm holding the propeller. This is the counter force of the propeller. When I hold the rotating propeller, it tends to do this, right? It tends to go the opposite direction that it is rotating. Alright? So if I rotate the propeller, the propeller will give a small force so that the drone rotates in the opposite direction. Sorry? Yeah, like this. So imagine that when you rotate in one direction, the drone goes in the other one. That's force and reaction. And, well, if you put all the motors to run in the same direction, what would happen is that you would have a crazy drone that rotates along its own axis really fast. and that wouldn't give stability. If you remember a helicopter, the main reason why the helicopter has that back propeller here is to compensate for the force, the torque that this propeller here, the big one, does in the helicopter. If the helicopter didn't had this propeller, it would rotate crazily along in this axis here, all right? And that's not good. So how the helicopter does to go to one direction and the other is increasing and decreasing the force on the back propeller, okay? So it makes like this, increasing force and decreasing in the back, all right? So in drones, we cannot do that because we don't have propellers in other direction than this one. So we take advantage from what I have just explained, this counter torque that happens. And the good thing about it is that the way the propellers are distributed is that you have one clockwise, this one is counterclockwise propeller, and the other is clockwise. And the next is counterclockwise, clockwise, counterclockwise, clockwise, and that's how it is. You have three counterclockwise propellers and 3 clockwise propellers. And when you are rotating all of them in the same speed, the torque applied to the center is 0, right? Because if one tries to rotate it in one direction and the other in the other one, it stabilizes. So we have 3 pairs of propellers acting upon the drone. So when we want to rotate along our own axis, what we have to do is differentiate the speed from those counterclockwise propellers to that clockwise propellers. And the way you do that is diminishing the speed from 3 of them and increasing the other. If you want to go to the other rotation, then you do the opposite. And that's how you control the yaw. It's magic? No, it's math and physics. So it took me some time to understand how it worked, because it's really different from what we are used to, you know. But it's really awesome to know that this happens, and that's why drones are really, really cool. You don't have to put propellers in different directions, and they just work. Okay. Let's go back to desktop. Okay then. So we made sure that the motors are stopped if they are not armed. And now let's start our control. Okay. So, in order to control our drone, we will have 3 different PID to control each of those axes: the yaw, the pitch, and the roll. Each of them will work simultaneously and separated from each other. So the yaw won't change anything on the pitch, that won't change anything on the yaw encode, right? But when you change the pitch, the yaw may change a bit, but the idea is that they all work separately, right? I will explain how PID can be computed here, but keep in mind that this can be used for many other things and many other controls. And what I'm going to do right now is explain really fast about PID. But if you want, you can go to my YouTube channel. I have a video explaining PID that takes, I don't know, 1 hour. And it goes through all the parts from understanding PID to implementing a basic PID and then implementing a class, a PID class, right? I will only do it here really fast because I'm used to it, so you can then implement and understand better. But here is my YouTube channel. It's /Ivan Sato, the same as live coding, or if you are watching in the YouTube, you already are in my channel. There are some videos about Arduino here, and this is PID. It's 40 minutes, I guess, no, 37 minutes. And it works. Anyway, going back to the code. PID is basically an algorithm to do control. To control and maintain a set point, a desired set point. The set point in this case will be our desired roll, pitch, and yaw. So when you, for example, give the drone some inclination to the front, when you send that command, you are saying, I want you to change your set point to something other than 0. In case of going front, I want you to keep the inclination in the pitch axis 20 degrees, and that's what the commander will tell the stabilizer what to do. So here we will need to store the desired roll, pitch, and yaw. And what better than the drone object to store those stuffs, right? So we can store we will create here a floating point array with 3 elements, and those 3 elements will hold the target yaw, pitch, and roll. Alright? Remember, our yaw, pitch, and roll in the drone is in degrees. So all math we are doing is considering degrees. Let's initialize the target with 0, 0, 0. Oops. And this is what we are reading to see the target in our drone. So where am I? Okay. So let's implement only for X here, and then we encapsulate that inside a PID class and do to the others, right? The target PR0 is the Y, the yaw target. But the yaw target is different from the others because, let me switch my cam here again. Not this, not question, okay. When you set the control, let me get a control here. Wait. Okay then, just for you to understand, I have here the control, this is a turtle. It's how much speed you give to everyone. All right. So when we set the target, we will need to set the target angle in yaw, in pitch, and in row, and also the turtle. All right. So we have 4 commands: 1, 2, 3, and 4. The turtle goes from 0 to 100, or whatever value you want. The yaw in this case is going up and down in the right stick, and the row is going left and right in the right stick. So when you do this, you are actually doing this in the drone. Imagine the drone here, fixed. You are moving the drone in this equally there, right? Let me put it a little back. So back, front, right, left. But the yaw is different. When you set the yaw to right or left, the drone won't do this and this. When you set the yaw, you're actually setting the angular speed of your drone. So when you turn right, you're actually saying, okay, drone, I don't want you to be in this direction anymore. I want it to be this, and you go changing each time more and more. And well, that's the idea of the yaw. And the turtle increases the power of every one. Now let's implement this. Okay. All right. So we are missing something in the drone. The target YPR, I will change to target state. All right. But we won't store that in a floating point array. I would like to create a new structure which is called target state. Not state, but something different and better. Target attitude. And inside it we shall have a float yaw, a float pitch, a float row, and a float tar. I don't know how to write this. Google will fix me. It's not turtle. Google, you are wrong. Turtle, yeah, not turtle. So in our drone we shall have a target attitude, which is called target state, and here drone target state and target attitude. I don't like attitude. Let's put state. I'm really undecided. The type should be state. Target state. Attitude only consists of orientation, if I'm not mistaken. Alright. So the target state is defined. Let's see if it compiles. It's missing this. Okay, it's working. We don't need this line here. Alright, so in stabilizer, let's do it for the pitch. Alright, and how PID is computed is using basically the delta time. So we need to know how long time the value, not the value, but how long time since the last update in the PID. So let's start here, unsigned long last compute time is equal to 0, and first we find out the dt, which is the delta time in seconds, right? So to find dt, let's get the current time of the microcontroller and let's compute the difference. Alright, so let's do dt is equal to now minus the last compute time, and this will give us the delta time in milliseconds, because milli returns in millis. And what we do here is to divide by 1000.0 to make sure it's a floating point and it's not casted. And here is something really important. Okay, we cannot continue on doing calculations if dt is too large or dt is really low. So we must check and if dt is good to go. So if the delta time is less than or equal to 0, this should never happen, right? Because we are not calling this method more than once in every 10 milliseconds. But let's just consider that, because we will be doing calculations that will use dt as the divider. So we will divide by dt, and if we divide by 0, then our microcontroller hangs, and that's not good. And we cannot use dt as a large value, because we need that dt really fresh, right? We need to update this every 10 milliseconds. So if dt is larger than, I don't know, maybe 200, 0.2 seconds, which is 200 milliseconds, then we should, I don't know, let's for now just log dt to high and log the dt. So if this happens, it means fuck, we are not being able to compute and stabilize the drone really good. What can happen here, and I will just explain you the reason why, is dt be greater than 0.2 when we start stabilizing. And the reason why is because we are returning from this function if the state is not armed. So if the state is not armed, we won't be updating the last compute time, right? So that's bad. And the way we fix it so that when the first time we run it, it is indeed fresh, is to keep continuously updating the last compute time before even returning. So let's save the last time as now, and that's it. So we check DT after, right? Because if the drone is stopped but DT is high, whatever, I don't mind. And let's log DT, and that should work. Okay, so to calculate the PID, I need 3 components, and I need 3 constants. For a while, I would place it here. The constant for proportional, integral, and derivative. I will define Kp as 1, Ki as 0, and Kd as 0 as well. Let's put 1 in everyone so that you can understand. Anyway, and we also have the output from the PID. We have the P, the I, and the D. The P stands for proportional, and the proportional is basically the set point that we want to achieve minus the real state. So imagine the P being the target state of the pitch minus the real pitch. So the real pitch is inside drone, and the target state is also inside drone, target state dot pitch, and drone YPR 0, which is the pitch. Alright, no, it's not the pitch is the 1 index. So 0, 1, 2. The P is the index 1. So this is what we call the error. Alright, the error is how much wrong you are. Alright, and when you are wrong, you want to correct that, right? And that's why the P is the proportional to the error. So we multiply error by Kp, which is basically, okay, if you are wrong by 100 degrees, then the proportional system will set it to 100, right? Kp will probably be lower, but let's keep it like that. And the other one is the integral. So when we integrate some value, we are actually summing it in time. And there is a problem if we only do like this. Y is equal to error plus equal to... Sorry. Y is equal to Y, the last Y, in this case, we cannot declare the PID here because it will be 0 every time we run, so let's declare it outside. So it will be I plus the error times Ki. So Ki is 1, so it's basically summing the error. But the problem here is, imagine that, let me draw a timeline here. Look at my beautiful timeline. Okay, imagine that you are running the control every, let's say, 1 second. Alright? So every 1 second, this is 1 second, you take a measure. So you take a measure here, you take a measure here, you take a measure here, here, and so on. And when you take that measure, you are reading something like, okay, I am at angle 0, I am at angle 5, I am at angle 0, let's put 2 here, and so on. So when you are at this angle, knowing that your target is 0, and you are wrong for a second, the error here will be 0 less 0, which is equal to 0, right? So the error is 0. And if you integrate this error here, let me put the error here. The input, the error will be 0. And you will sum it to the integral, and it will be 0. And when you integrate that, it will be 0 here as well. And here the error will be 0 less 5, right? The target is 0 minus 5, and it will be minus 5, the error. And when you integrate, it will be minus 5, and the error here will be 0 minus 2, and when you integrate, you will have minus 7, right? Because you are integrating 2 as well. And if you start going the opposite direction, let's put minus 5, then the error here will be 5, which is 0 minus minus 5, and the integral in the next state will be 7 plus 5, which is minus 2, and you start to stabilize. Anyway, I'm writing this because imagine that this is one sample per second. And what this measure here says is I am wrong 5 degrees for a second, right? But what if you start reading more samples per second? If you start reading more samples per second, you will notice that you are actually double integrating what you are doing. So let's say here we read 5 again, there will be minus 5, and here the integral will be 0, but here it will be minus 5, and in the next one it will be 10, and you are actually increasing your error, your integral, because you are changing how many samples you are running. So anyway, this is not a good graphics at all. If you want to learn more about this, you can go to my video. It's in Portuguese, but you can translate it to put subtitles in English. But what we have to do is to normalize with the time. So imagine that if we are running 2 samples per second, each sample should be weighted as half, right? Because each sample has half the importance, because we are reading 2 of them in the same second. But we are running not 2 anymore, we are running 4 samples. So each integral should take a pondered sum of that delta time, alright? So that's why we multiply, when we integrate, the error times the ki. I won't be multiplying right now, alright, by the ki, but you multiply it by dt. So that's basically a way of neutralizing the time taken, alright. So let's imagine that we increase to 20 here, dt will increase, which means that we will have less samples, but each sample will be more important. Will double its importance, right? So that's the reason why we multiply by dt. And the derivative, okay, the derivative is basically how our error is changing. And to know the derivative, we need to store the last error. Alright, the last error is important to the calculation because the last error is basically our way of finding how much error is changing in time. So if the error is changing a lot in time, it means our system is highly unstable. We may want to sum or subtract that in our final PID calculations. So the error that we have right now minus the error that we had is our derivative. But remember about the importance. If you are seeing the difference, so the difference between here and here is difference between is different than calculating the difference between here and here. And instead of multiplying the error here, you divide by dt. And that's where things could go wrong if dt is less than or equal to 0, right? So that's why we check for that as well. Basically, that's the derivative, the p, the d, the I, and the d. And in the end, what we do is to sum everything. So we will have a float PID, which is equal to P. Let's put the constants in the final formula only. P times Kp plus Y times Ki plus D times Kd. And that's how we sum everything together. A problem that may happen here is that y can go up and up and up and up and up, and that's bad, right? That's really bad. And imagine something as well. Imagine that the drone falls. Probably y was really high because it was wrong for a long time. And when we try to fly again, y will be high. So it may make the drone crash because the y was not resetted. So where is a good place to reset the PID? Well, every time the drone is not armed. You constantly disarm it or reset it. Alright? So here we stop the motors and we also reset I. Alright? We don't need to reset D, but we can set the last error to 0 as well. Make sure everything is fine. The P is not necessary because it doesn't consist of any other data than the actual data, right? So that's why we don't need to reset the D. This is the PID for one axis. We could copy this and paste 3 times or 4 times or 5, 6, 7, but this is not good. This is not good because it's not maintainable. If another person took this code to read, it would not be understandable. We are creating thousands of variables here that we'll have to copy and paste, and that's not good. That's not cute. That's not beautiful to read. So let's make it beautiful to read. How to make things beautiful? Here, let's create a class, and a class called PID. The class PID will consist of something that I already made. So I want to reinvent the wheel here. I will only get a gist that I already have made. GitHub. Oh my god. I am transmitting for how long? Whoa. I am transmitting for 7 hours. Yeah, that's a long time.
Almost 8.
Almost 8? Yeah, almost 8. In 15 minutes it will be 8. Anyway, I have a class PID here.
Now 8.
Yeah, now it's 8.
8 hours and 1 minute.
Isso cansa.
Why there's the twin.
Você estava assistindo?
Yes.
Mas você não viu essa parte?
Eu vi. Mentira, não estava assistindo, eu estava escutando.
Então você não estava escutando.
I heard you picking it there and explaining how the
As
throttle.
pessoas estão te ouvindo.
Whoa, there are people hearing me. Brazilian code.
Yeah, where are you from, Brazilian code? Where are you from, Brazilian code?
Oh, I have an honor.
Ok. Acho que vou fazer uma pausa. Minha garganta está tensa. So I'll make a little pause now, drink something and eat something. You should go to the bathroom right now if you want. And if you have any questions, any suggestions, I'm here reading the chat. Olha que bonito. Questions. going back right now. So for the ones who are new in the room, we are implementing a drone firmware. We have explained all the functionalities and what's necessary to make a drone fly, and we are implementing the firmware right now. We are in the last part mainly, and this is the drone we are working on. This drone is really small. It's a hexacopter, a mini-hexa, and this is the circuit that we are using, and it uses MPU 6050 with SPM so that we control it from distance. We have implemented the attitude, we have implemented the orientation, and we have implemented alarms, we have implemented battery checker, we have implemented the motors, the system, and I mean everything it's in its place. Okay, now what's missing? It's probably not probably, but certainly the PID. We explained how PID works, and it's time now that to make this PID be more maintainable. I won't implement something I have already implemented because I already have a PID class. So it's in my GitHub, in my gist. Alright, so let's skip this class in 3, 2, 1. Ready. Add new sample, adds a sample or sets the sample of the PID. Set point basically sets the set point. When you instantiate the PID, you can set the KP, KI, and KD. And we also have the process which calculates the DT, the delta time. But something that I want to do is to allow the delta time to be passed in, so as a floating point, because we have computed it already, right? And the idea here is to only get the delta time from when we process. The result is then returned as the PID, the sum of everyone, alright? And there is something missing here that is really important, which is a Y limit. And the Y limit is an important thing if you don't want your PID to go crazy. All right, so the Y limit will be saved here, and in the process what it changes is basically check if the Y limit is greater than, if the integral is greater than the Y limit. If so, Y is equal to Y limit, and check the negative value as well. If Y is less than minus I limit, and if so, Y is equal to minus Y limit. I can do this in one line for each one, so it will be easier. So Y is equal to Y is greater than Y limit. This is a question. If the answer is true, then we set it as Y limit. Otherwise, we set it to Y. Oi? Oi? Ah, não tô no desktop, né?
Nunca deu order.
Tá tranquilo aqui. E ele tá piscando, então tá funcionando.
Yep.
Só que não tava no desktop. Damage. Vamos esperar ir pro desktop. Ok. Oh, sorry, I have just coded a few things without showing the desktop. Yeah, I'm done. But well, what I have done here is to pass in the delta time to the process, and we are now limiting the y positively and negatively to this value y limit, and that's basically it. If it's less than minus y limit, then minus y limit, otherwise no. And let's put a space so that it is aligned. Compute delta time, the derivative, save the last sample, sums everything, and returns the PID. That's basically what we need to do for the PID to work. Now let's instantiate our PIDs. So we will have a PID for the yaw. So let's call it PID yaw. And the PID yaw will be 100. It's good to start the y and the in 0 and then go increasing it. And our y limit will be around 50, 100. I don't know any value. 100. Let's have a PID pitch and a PID roll. I will reorganize. Okay. The PID pitch, row, and yaw. And now let's update all those PIDs. And we forgot to skip if the delta time is too high or too low. Now we compute the PID for each of the axes. In the case of the pitch, the PID pitch, add new sample. Alright, and oh, there is something wrong here. There is something wrong. This PID class that I implemented was not supposed to be on a bigger project, so we need to instantiate only the methods here. Let's do it now. Let's copy. Let's create new file. pid.cpp. We don't need pragma ohms. Include types, and also include pd.h. We don't need other than that. And let's implement all the methods. First one, turbo pd process, pd set point, pd add new sample. That should be it. And now let's remove the implementation from the header file. Okay, so now we have the header file and the PID class implementation. So let's include, oops, not here, the stabilizer, the PID class, and also in EasyFly. So let's compile and see everything that went wrong. And magically there is something wrong. Okay. So in the stabilizer we don't need PID anymore. The add new sample supposed to be the current pitch, and the current pitch is inside drone, ypr, in this case index 1. The first index 0 is yaw, the second is pitch, which is 1, and now we add everything here. Drone, row, and the difference from the row and pitch to the yaw is that in our controller, in the commander, when we set the value of the yaw, we are actually going to sum that value. So we will be changing the target yaw every time we change it. So, but the computation will be the same. The PID will try to maintain the stability in all the 3 axes, okay? And then we compute everything. So let's compute it with the delta time we got. So let's create a float here. Yaw out yaw out row and out pitch. So we are now getting all the 3 values outputted from them, and how it is going to work to get those values and update the motors. Okay, that's interesting. That's the interesting part. And in a simple drone, all right, in a quadricopter, how many propellers does the drone have? We have six, not 60, 6 propellers. Can you see it here? Not me. Here. We have 6 propellers. Yeah, you see 6. You are right. Not question. Okay. So the difference between a quadricopter and this one is what I really want to implement something generic enough so that you can have any number of propellers. Alright, so let's imagine a perfect world with 4 propellers. Okay, they are displaced. Let me get a pen and draw this in the right way. So I have done this drawing before. I will redo it now. Okay, so as you can see, I have a white paper. Alright, so imagine a drone with 4 propellers. When you want to rotate along one axis, in case this axis here, alright, let me do it with the stronger pen. Along this axis here, what you have to do is increase power in this propeller, so you increase power here, thank you João, and you decrease power here. And if this is a drone, okay, it will do like this. If you do the opposite, going down, start off up, going up, it will go the other direction, right? Question, where can I get the components to build myself one and replicate this project? This project is not open source yet, but it will be in a few weeks. Okay, the components you can buy on AliExpress or Deal Extreme. You only need a 80 mega 328. You need a GY88 and also an ESP, and you need to make the circuit board, and everything is about $20-30, I guess. That's how much you should pay for building yourself. So okay, I want to rotating this axis here. Basically, imagine that I had another propeller, alright, right here. This propeller and this propeller have the same impact on this axis, right? So the thing is, if you increase this power and this power equally, and you decrease this power by x, and you increase this power by x, and you increase by x, you will have 2x on one side and 1x in the other side. That won't compensate and be strictly in the center. So you need to calculate the pondered values of each one when you are doing this. And how you do that is by calculating the distance. That's something I thought about today. I'm not sure if this is the math, real math that is used, but I haven't seen anything generic enough, so I'm building myself the generic way of doing drones in whatever shape you are. So you can calculate this size here, right? But something that needs to be compensated is for the number of propellers. But in case of drones, where you usually have a symmetrical shape for the propellers, alright? That should be fine, because if you add x here and you add x here, you will have 2x in one side and 2x in the other side. But imagine now this other situation here, where you have this kind of situation, and we are trying to rotate in the red axis, alright? So if we follow the rule of the distance from the axis, alright? If we follow the rule, the distance from the axis to these two motors is 0. So basically, if it's 0, we won't impact these two motors because it's 0, right? The distance is 0, so anything we calculate will be 0, right? So now let's think about a bit more. The distance here, if you imagine a circle, oh, beautiful circle, almost. It's not the maximum, all right? So the maximum is here. It's here. If we had a quadcopter superpositioned inside here, it would be a little distance, a little more distance than this, right? So basically, we want to know the distance of this to this, okay? Distance from this to this. Now, just so that you can understand, if I had another propeller here, I'm getting confused, but it will clarify in a minute. If you want to rotate along this axis, this propeller here would need to make a really large amount of speed to compensate for that. But it is really close to the center. So you basically distribute the power based on the distance. So the ones that are more distant from the center, not from the center, but from the parallel line here, in this case it's this line, we'll get a higher value. So if we simplify that and we use it as a pondered sum of values, you would have something like output going from minus 100 to 100, and you need to distribute this into all the propellers. Alright, so let's make something generic enough so that we can work with any shape of drones. And when I say any shape, I say something like this. If you want a drone like this, okay, I want this to work as well, and this is the center. So let's make it work for that. I'm not sure how to do that yet, so I'm thinking. Maybe this. We could have an array of propellers that define the position x and y of each propeller. So basically we are mapping each propeller with an x and a y. Since our coordination or we are using Cartesian, we can say that the center of the drone is in the 0, 0 coordinate. So the distance from the y-axis to this point will actually be x, right? If you put x as 0, the point would be right here. So this is always x. And we also need to think about the other situation for the row in this case. This is the row actually. For the pitch, we will be calculating the distance to the y, but it's actually the real y here. And that's really interesting. So if we map every position of the propeller, imagining that we need to distribute 100%, something that goes from 0% to 100 in all the propellers, alright? So we have a x component that goes from 0 to 100, and we have a y component that goes from 0 to 100, and that simplified becomes 0, 1 to 0, 1, alright? And we want to distribute the weights for each propeller. This is something that can be done in the beginning of the program. It's not something that we need to calculate every time because the shape of the drone will not be changing, right? But basically, It is really simple. Now it's clearing my mind. So if we sum all the x's and we divide by the x that we are checking, so let's say this x here, the weight will be equal. The weight is a two, it's a matrix, it's an array of two positions. The weight would be something like the weight x would be the self-value of this divided by the sum of all the x's, and the y is the sum of the y's. Alright, that's how the weights are computed, but this only works for the roll and pitch, not yet for the yaw. So let's implement this in code, make this work in a generic way, alright, and see how we can extend this to the yaw, because the yaw is a bit complicated. We would need to compute the torque from the center, and I don't fucking know how to do that, but we can try. So switching to my desktop. Okay. Alright, so stabilize. Let's define our drone shape. Something that should not be here, it should be in the config. So let's put in the config. So the proper position will be an array of arrays, and acho que isso vai dar certo, cara.
Vai, dá certo mesmo. Muito difícil. Muito difícil isso.
É diferente. Let's see how much we did it. Eles não usam o XY, eu acho que eles só usam o ângulo. Vamos ver aqui.
Eu sei que tem um custom map, porque para o meu pai ali, por exemplo, eu preciso fazer um mapping custom, porque ele não é tipo um X, sabe?
É muito confuso a multiplicar. Okay, so here's multi-way firmware. As you can see, it is doing pretty much what we are doing here. And this method called PID mix is what you pass on with the X, Y, and Z. X is basically the position X of the motor, Y is the position Y, and Z is the position, not the position, but the probably the direction, right? So as you can see, it is only +1 or -1, all right? And you could compensate that with 0 point something. But this seems a really cool idea. And basically what it's doing is getting the command of the turtle, which is the turtle value from the command, and summing with the PID from row times the X component plus the PID from the pitch times the Y, and the yaw direction times the axis PID yaw times Z. The yaw direction is probably a definition if it is positive or negative, so that you can, yeah, probably it is. Let's see here. Yeah, yaw direction. Not used anymore for several. It's fixing. If you want to reverse the yaw correction direction, so basically it's 1 or less 1. So that seems a really cool idea to use, but we have explained it here how it works. Basically, for the yaw, they set a value of 1 and -1, but that seems okay for me. So let's see how we define all the positions here right now. We could do an array inside an array. So in our case, we shall have the propeller. We'll have 6 propellers, and the first one it's 0. The X is 0, and the Y is, let's measure and put in centimeters or millimeters. Where is my centimeter? So it's 67 millimeters. Let's make that 100. So no, not 100. 1.0. Let's make the maximum 1.0. And then going from this to this, we shall have a 60 degree angle. And so the X will be basically the sin. The sin of 0 is 0. So we can generalize this with sin of 0. Let's define degrees, not degree radians. I think C++ has something like that, but let's implement. Radians is equal, not equal. Let's define 2 radians. It's the same as 2 radians degree. same as degree and 180 divided by n pi. So it's the inverse. Let's see. Times pi divided by 180. That's right. So here is the same to radians 0. And same, this is the cosine of 0 as well. So cosine of 0 is 1. Alright, this should be 1. The sine, we can use this template for all the propellers. And just update the angle here. 60, and then it's 120. $120. $120, then 180. And then we have 180 or minus 120. That's not a problem. And then minus 100, minus 60. So that's our configuration. Let's align everything. That's fine. Yeah, we have defined the state of our drone. If you had any propeller, why don't drone ever have props mounted? Hello Cam White, thank you for spamming. Thank you very much for spamming.
Someone is spamming.
Okay, that's a pretty happy face. I won't get mad with you, but I will have to scroll up to read.
Não acho que eu tenho companhia. Entendeu?
Cadê Core White?
Não
I won't ban him if he... Why did I come back? Okay. I just want to read. I found the upside down so that we can... Okay, that's a good point. Blow scan. Come on. I'm not sure if the math library has the 2 degrees. I don't remember. It seems not. Yeah, so there is no 2 radians method in math, I guess. That's how we are going to use it. So the position, and also how to implement this in a good manner. Let's save the weight of the computer value. In this case, 0. Zero will be liquidated, so we need to actually define it. Change it from const to float, and it will be on the memory, but that's not a problem. Let's see if it compiles. Okay, prop position as memory must have bounds. What? Must have bounds for all dimensions except the first. Okay, so the bounds are 3. It's just that you want. PAD row was not declared. Okay, so it worked. PAD row, PAD row, PAD row. PAD row, haven't you been declared? Ah, pin row. Okay, so it's right now. So let's go there and mix everything up and output to the motors. Alright. So now let's iterate through everyone. The size of complicating proper position divided by, no, I cannot do that. I'm not sure I can do that. I will do a iteration and define proper count is equal, which is, and this shouldn't be here. Let's put it right on top. To math. Okay. So the proper count is a number 6, and in this case, can I put it here so that we guarantee that we have 6? Are we Arduino claiming? Okay, so work it. And now we go through proper count. Plus. Okay, so let's compute the weight of each propeller. Okay, so basically we need to sum everything. What is program for completer? Completer. But if we sum everyone, the sum will be 0. We have to sum with the absolute value, because imagine, yeah, it's the okay. So if we sum in a perfect drone all the x's, it will sum to 0, because this is positive and this is negative, so they will always cancel. But if I sum everyone, okay, and if I sum everyone but the absolute value of the x, that will give me the total of the whole x. And imagine that we have only 2 x's, okay, so let's imagine only these 2. If this is 1 and this is 1, they will sum, this is -1 and this is 1, sorry, they will sum to 2. And when I set the power, the weight of this will be 1 divided by 2, which is a half. And a half is the half of the power I need. And this one is half as well. So our math works. The sum here will be actually sum 0 is equal to plus equal to prop position y 0, but I want the absolute value of this, so abs of this, and the same with the yx, in this case 1. And in the end we need to iterate everyone so that we update the weights. Okay, so we do a iteration to sum and then iteration to compute the weight. So the propeller position y2, in this case we are accessing this value here, which is the weight of the propeller in respect with for the x we need another column for the y as well, so let's put here yes, I guess I can. 2, 2, 2, 2, 2, 2. Really complicated. Okay, so going back to my camera, I have added here the x and y. Okay, so let's put some header here. X position y position, x weight, and y weight, and remember that I'm from Brazil. So the x weight and the y weight will be computed and will be saved here. So the 2 will be basically the absolute value of prop position y0 divided by sum 0, and 2, 3 will be 1 and 1. Now let's see if we have to invert or not. So imagining this drone here, if I sum the axis goes to the y-axis, so they are inverted. The y-axis corresponds to the x, the y value is summed and it corresponds to the control that we are doing in the x-axis, and the y on the x, and the x in the y. So we need to invert here. So basically we can swap here, sorry, yeah, here. So we are swapping the X and Y so they are in order. But look, all the data inside here won't change at all. We are not changing our drone shape in the air. At least I'm not going to do this. But if you do, you have to compute the new shape every time you process. So let's do this in the initialization. Okay. So with our threads, let's do this and compute propeller values. Alright, so now we have a generic interface for all the propellers. We could manage to get anything for the drone to work. I don't see a difference, but let's complete it now. There is something missing, and in the motors that I'm not happy. Inside the motors, where is the motors? Not here, motors. Set power shouldn't be something like M1, M2, M6. It should be an array, right? So let's pass in, instead of integers, let's pass in an array of integers. Powers. And the size of this will be prop count. So we have to include config.h. Yeah, that seems okay. Now let's change this to prop count. And the cool thing about it is that we are already using powers as our main array, but the only thing that will change here is actually prop count, and here we should use this instead because it's an array. Anything else? I don't think so. Oh, motor pins. We should make sure it is the same size as our propellers. So let's go to configs, and where is motor pin? Let's put it below. Okay, it's below, so that in here we can have prop count. So that's all we have to do to make it work, I guess. It will have problems during completion, most probably. Yeah. Too many initializers for float. Okay, so we put 4 here. We added the weight. No matching function, set power, brace enclosed initializer. And that's because we cannot do this, we have to do this. I guess this should work. Powers is color, missing this. And magically we had a recompile. Multiple definitions of propositions. Awesome. That's not possible unless attitude. I I didn't define proper position in attitude, I guess. Attitude.cpp. I didn't declare that. That's really weird. Let's dig some more. Okay, so this is implementation. It's not a constant. Damn it. But if it's a constant, then we cannot do this. That's really, really bad. I will have to create, so just so that you can understand, this is something that should be, this is more implementation than definition, because this is not a constant. I'm not setting this as a constant because I need to change those values here. And I don't want to create another floating array or even allocate memory dynamically just to store this. So what I'm going to do is create this proper position, okay, inside the drone class, which is more intelligent. And so let's define this here, and we can put it inside drone prop positions, and here it will work. We only have to declare it, this after state. So static float array prop positions prop count and 4 propositions. Let's call it props. It will diminish the size. And we need config here as well. Okay, that's all we need for now, I guess. Let's go to stabilizer and change. Huh? Eight. And change the initialization. We don't have prop position anymore. We have drone props. Okay, that should work now. Good thing is that we have separated that configuration, and it's not anymore inside the config. And the best thing is that we are compiling. Yay! So I think I deserve some more cookies and some more stuff to eat because I'm hungry. Alright. Drinking something and going on. So we have computed the propeller weight values. We have saved it. Let's print all this so that we can debug. Alright. We can print inside here. So I'll print the index, but before printing it, I will print this and concatenate with this, and then print the x and y positive values. Okay, so drone props y 2 and the space, let's take it at 2D array, comma, and in the end close bracket and end line. Alright, so drone x2, it's missing the 3 here, and let's upload the code and see if it is being computed correctly. Oops, sorry. Okay, uploaded. So let's open the serial monitor. Shut down the drone and shut on. Okay, this is not correct. Let's shut down everything. Open the serial monitor. And now shut on the drone. And here are all our values. This seems to be wrong. Shouldn't be like this. Why are they summing up? Looks like they are summing up. So let's log as well. Let's log the actual position of the propeller. Position. Oh, I know why. It is right. But we are logging y plus 1, which means the 1 stands for, so it's actually 0.25, 0.12, 0.13, 0.25, 0.13, so it's working. Our logging, it's shitty. Mwahaha. So let's fix our logging and comprove that. So in, shut down, turn on, compile, upload. Okay, so it's working. Can you see here? Propeller 1, in this case, let's imagine that it is this propeller here. It has 0.25, it's the weight that it has in the x-axis, and as we can see, it is the distant one, right? So the other one is 0.12, so it's about half of the distance from the x axis. And then we have 0.13, which is a round problem, but okay. And then we have minus 0.25, and then we have 0.13 again, and then 0.12. And then for the y-axis, this one is superpositioned in the y-axis, so it has 0 proportion. This one is 0.25, this one is 0.25, and 0.25, 0.25. And the reason why we don't have same values in the x and y is because we are using the the y-axis aligned with two propellers. If we had used the half of it, right, we would have some really close values. And as you can see, if we sum everything up, it will sum to 0, 1, right? And if we sum here, it will give 1 as well. So we have a working model of the drone, and now we have to output those values computed in the PID to each propeller. Let's answer the question. Hi. We are using the 50 megabit at 8 megahertz. Yeah. Okay, so let's continue. I will remove the logging. And let's finally compute the powers of the motors. I will save this inside the array here. Powers. And in the end, what we will do is set motors, set powers. Alright. Let me just check something here. João.
Hey. to download.
O dele é 300 mAh e 30C. Acho que dá.
138 mAh. It's too low.
300 mAh, 30C o dele. Top lá pegar. É nessa rua mesmo.
No Piauí? Da FUC.
Só vai?
Só vai. Mas é com essa pontinha aqui?
É.
Como é que a gente usa isso?
Não sei. Eu tenho esse conector, eu acho. Este conector está em algum lugar aqui. Mas onde está o conector? Uma vez eu comprei ele, só que ele é SMD. É alguma caixa, cara. Tudo se encontra em caixa nesse quarto. É tipo, onde tá meu pé na caixa? É só achar a caixa. Mas, se pá dá pra botar um jumper aí, não? Deu? Deu? Eita. Ok, so we have a plane drone. Alright, so we are trying to arrange a battery here because the current one we have is a Chinese battery that drops 1.5 volts and that's shitty, so we are trying to arrange a good one. And anyway, going on, let's iterate and distribute power to propellers. For int e is equal to 0, y less than prop count, y plus plus. Now let's go and find out. There is something missing. Something missing that is important. We have to set at least if the x and y, and we also need the direction, the direction of the propeller. Okay, so let's set it here. Hello dude, what's going on? We are basically doing the computation of PID and outputting it to the drone. Have you just arrived? And this will be plus, this will be minus, plus, minus, plus, minus. Okay, this is not 4, it's 5. So now stabilize. We will go and set the powers y as equal to, in this case, rho is on y-axis, pitch is on x-axis. So if pitch is positive, we should multiply the pitch value times the drone props y x, which is 1, 2. Okay, so we are having a problem here It's not a problem actually, but let's define it. Define props x 0 y 1 propeller x weight is 2, propeller y weight is 3, and propeller direction is 4. And this is the mapping for each value inside these props. Okay, so 0 is x, y, x weight, y weight, and the direction. So instead of accessing them directly, we can now substitute it with prop y, x, prop y, prop x, prop y, again, prop y, prop x, and this is prop x weight. Let's change to simplify the text, it's too big and I don't like big strings. The weight of x, and here, oops, it's not. This is 3, so 3 is actually prop y weight. Remember that we swapped them because they need to be swapped. Okay, so no more 0, 1s here. Only here we can use prop x as well, but that wouldn't make much sense because we would have to use the same definition from there. Out pitch time drop up the 1 2 y x. So the pitch uses the x weight because the pitch is in the x weight. We shouldn't swap it here. We should only swap it here because the pitch uses the y component. That's more intelligent, I guess. So we can either make a really huge sum here, out row times props y propeller x weight plus out yaw times drone props y propeller direction. And that's pretty much it. But this we can normalize with the prop count, because as many propellers as we have, the yaw should diminish. If we have many more, we should diminish the amount of thing. But let's give it a try for unnormalized yaw. Props y prop there. Yeah, that's pretty much it. I think we have completed our drone film. Is there anything else missing? Oh, important part. The part where we control our drone. It's a simple part. It's not so important. No one wants to control a drone. People want the drone to fly by itself. So Let's debug this and test it out. Oops, we have a problem. Too many initializers for float form. 6, 5. That shouldn't be happening. Okay, I know what's wrong. In drone we have defined it as 4 and now we are defining it as 5 here, so it's a mess up. So plug USB, open port, turn on EMU, turn on quadcopter and upload. Last compute time is in stabilize. Okay, so we need this. Okay. That should do it. Why is not declared? Okay. Oh, good thing. What is missing here is to reset our PID. So let's go through PID row.reset, and this method reset doesn't exist yet. So let's implement the reset method inside PID. Put it as first thing and implement the reset method. Watch PID reset. And what we do here is set Y as 0 and B as 0, and let's set B as 0 as well. That's so cute. Okay, so let's upload, see if it compiles. It compiles, that's magic. But it's not uploading, so compile again and upload. Yeah, it's uploading. We are using 68% of the memory. That's sort of reaching the limit. Okay. So let's turn off, and reconnect again. We are having some problems in the serial communication. I don't know what's the reason. Okay, it's working. Let's ping the MPU. It's working. And now let's arm our drone. Okay, nothing is happening. That's expected. We don't have any connected motors. And now it's time to call my friend to solder the broken wires. João, partiu soldar fios? Ok.
Ok.
Quero fazer voar, cara. Em teoria está tudo pronto. 100% e melhorado. Simbora.
Let's see.
Okay then, guys, this is not the end yet. I will open it for questions, and I will place the camera so that you can see João Pedro soldering the drone. I'll go to my friend's house and see if he can lend me a battery so that we can test it out, because the battery, as I said, is a Chinese battery and it doesn't support the current we need. Feel free to ask questions and also to do some suggestions. I will publish this right now on GitHub, okay? So you can read it, you can suggest things, and try to improve it. What I am going to do now is go to my friend's house, so I won't be here, but the streaming will continue, and I hope that today we fly this drone. I'm not sure if it's going to be achieved, this target, this objective, but we will try. So let's push it to GitHub. And let's put a README here. Another drone firmware. This is a simple drone firmware developed in a live coding. It should work fine. Any normal drone that doesn't
Use brushless models.
Use brushless models or changes its form during flight. Hardware. So I call it Easy Fly. Does anyone has a better name than this? I'll give you all 5 minutes to think about it. So hardware, to do share electronics needed. This could work just fine with any 8 megahertz, 80 mega, 32 weight, or any Arduino bootloader. This is an ongoing project. So I don't put this here. To work with fine bootloader. The drone layout. We have a really generic implemented, really generic drone layout setup. You will find it in drone.cpp. These are in...
Achei a caixa.
Achou?
No blog da bateria, pô.
Starter kit. What do you mean by that? Arduino kit. You mean? Achou a caixa? Tá aí? Ah, essa mesmo. Isto. É esse daqui, não é? Mas é tenso soldar. Aí vai ficar enfiado assim, ó.
Vou soldar isso aqui. Eu tô procurando o terminal, pô.
Terminal?
É. Esse aqui.
Não tem do 2 aí?
O clipadorzinho de dentro.
Ah, não, usa alicate.
Não tem nada de clipar dentro. Não tá aqui, não é aqui, não é aqui, não é aqui.
Eita. Grimpar. O de grimpar
fica no conector do terminal.
Não, fica nessa caixa grande. Fica na caixa grande. Yeah, I'm looking for a kit with low good. Cost like é proese.com.br ou proese.com? .com.br. Okay, so finishing documentation. Okay, so we have a documented thing. Oh my god, a lot of repos. Add to root. It's inside projects. Republica. Easify. Documents, Easify line. Okay, create repo. Okay, so let's see if the readme is okay. That's awesome. So initial commit that always have the commit message, and let's publish. I love you, GitHub. Description simple and just another drone. Publish. Okay guys, so you can get a code as it is right now in my GitHub. Yeah. Oh, it's private. I didn't know I could have a private. I don't want private. I hate private. No, make public. Yeah. Please type in the name. Okay, Fly. I understand. Confirm. And he asked my mother name, my father name, my birthday date, and now it's public. Okay then. So here's the link, guys, and I will let you see João soldering and almost burning its own finger, while I will go right next to my house and try to get the lipo battery with a friend. So this is João. He's not a Chinese, but he does Chinese work.
No, I don't do Chinese work. So, hello guys.
Let's set this thing here.
So here we are. Going to check it. Like, yeah, we have this right now. As our batteries are not very good. Like, they're these ones, so we cannot use them in our project. So we're using this power source to, this power source here to provide power to the board. And what I have to do now is to fix the motor, the wiring of the motors. Some are not very good. After a month, like, stopped, some motor broke the wire, so I have to fix it now. So while Ivan can get the battery at his friend's house, I need the third hand. Have you seen it, Ivan? The third hand?
Yeah.
There. Is it there? Yes. So, talking again about the drone and its board, we tried to build it as much as DIY as we could, and we ended up doing it like in a single layer, as you can see here. The dance board has a lot of components on it, but it's working pretty well for now. Yeah, I fixed one of the motors, so just the other that is in fact without the connection. There we go. Just need to solder this other one.
Não tem tipo 5 segundos, não é lá não?
Ai, que não. Bom, vamos tentar aquela de 138 bits. Só que vão ser bom.
Mas volta a descarregar, carrega ela então.
Where is it? Como você sabe que está descarregado?
Pra testar se funcionou, usei o multímetro. Tava com 3.7.
Então descarregado.
Aqui.
Então, carregador.
Deve estar na caixa de carregador. So right now the coding has ended and we are fixing some motor wires just to test the drone. So yeah, finish it.
Clicar o link.
Bota na tela. Digita no Illustrator. Digita no Illustrator e bota na tela.
Ok.
Working on hardware. Get the link. Coding has ended. Working on hardware. Daí bota o GitHub embaixo. get the link yet? We don't.
Well, I've now ended soldering the remaining motor wires, and we're figuring out how to power the board with other batteries I have here. We maybe try with True S to sell lipo battery, but I only use like one cell, or a small one cell battery that we have here, but it's not charged, so you have to charge it.
Não tem adaptador para ligar na tomada. Ah, liga não. Muito bom. Lost.
I stole it. So yeah, this is the battery that I'm really trying to use now. Because these was the last ones. And yes, just they didn't work. They are Chinese lipo batteries, and they were pretty bad. Cannot say another thing. We have like 4 of them, and all of them are shitty. So we are trying to figure out how to power the drone again. We are now using like a power supply just to test it and for Ivan to program it. And yes, it's something like that. Just to say to you again, for those of you who are new, we developed like a lot of prototypes. This is the first one. As you can see, it's like heavy, and it's like with big arms and kind of things, and massive body and this. Then we thought, no, let's make it lighter. We did this one, and this was the second version of it. And we thought about putting some holes here to pass like a battery strap, and we made some narrow arms. Yes, this. Then after that one, we did this one that is now broken because we ran some mechanical tests with it, and our mechanical tests were just throwing it in the floor. So if it breaks, we know the place and we try to fix that in SolidWorks or something, or our 3D software. and they have like more versions. There are like more versions right here. This one is just another one of this. We printed it to just to show at an event. These are the same. This is the second version that came from this one. The third version, we then figured out where were the weak points of the design, like here in the corners of the hexagons. So we made it like fillet in the corners. This one we cut it here to allow some soldering at the board. And then we jump to the last version, that is this one. This is the same version but just in black, and this version has like some clamps to the PCB, so we can fit the PCB inside here, and some place to make the PCB stand on, so it can clamp right to these things here. And another modification we made, another change, is in the motor housing. We have a square in the bottom, so we can pass the motor wire through with its connector, and so you don't have to pass the motor wire first and then solder it to the connector. That's it. And these are the mechanical versions. I explained about the board right a little time ago, but I can show to you again. This board has an 80 mega 3 tube 8. It's with Arduino bootloader, but it's made to work with 8 megahertz. And we have an IMU that is the Chinese IMU, inertial measurement unit, and it's the GY88. It has an MPU 6050 from EvenSense, that it's the accelerometer in the gyroscope, and a compass. I don't know the number right now, but it's an IHMC, something like that. And it has a barometer. It's an air pressure sensor, so it can sense like some altitude and difference in pressure. To communicate with the drone, we're using an ESP8266, that is this guy here, and what it does is that it creates a Wi-Fi, and we can connect to this Wi-Fi and send commands to the 80 mega that is running the PIDs and controlling the motors. The motors are DC, so only 2 wires and continuous current. So to power them, we just use some small transistors that are BC637, and they can handle up to 1 amp, so that's just what we need. And we control it through PWM, so each motor has 1 transistor to fire it up. We don't need to reverse the direction of a propeller or the motor in a drone, so we just need one to like turn on and off the motors. And we have another thing, that is an FTDI to upload to the board, and that's it. The board is a single layer board. Of course it has some 0 ohm resistors that we needed to get it done, but that's it. That's what
Bora
it has now.
tentar botar em paralelo?
Acho que não tem conector. Se o Marcelo não dissoldou e guardou em um lugar certo, sumiu o conector.
Aquele era pra série, né?
É, mas não. A gente fez para os dois ao mesmo tempo.
Ah, é porque...
Não.
Não.
A gente fez ao mesmo tempo porque é fácil de dissoldar e fazer assim de novo.
Nada, tá aqui, certeza. Tá aqui. Ainda tá aqui sentado.
Sério?
As for our, we're going to give our Chinese batteries another chance, but now we're going to put 2 of them in parallel to have more input or current flowing through. So I'm going to make, like, say, parallel motor connector. I need one of these. Then it's like in some of the boxes, or inside the, I don't know.
Right?
No. Let's open the lipo sector, cap the other battery.
Tem mesmo?
Yep.
Você não sabe se tem ou tem?
Tem, porque eu acabei de guardar. Mas eu não sei se eu posso ter guardado na errada. I don't know. Podia ser nessa aí. Eu acho que eu guardei nessa aí, mas eu não vi ele depois quando eu procurei.
Você tava na sacola ou não?
Não, tava solto. Não é tudo maluco. Vocês estão com fios.
Tá nessa daí, eu acho.
Now searching our boxes to find the connector. Yep. And I'm going to assemble like a small joint to put 2 of these batteries in parallel so we can maybe run the drone today.
I'm fucking angry.
I'm twice fucking hungry.
Criar uma pool aqui.
So right now it's again harder work. This is not the tool I want. Yeah, this is the tool. We have an error.
Huh?
Error.
8. Está streamando. Is this streaming? Here's the problem.
Oh shit.
Mas foi agora isso. Está streamando.
Again, we are working on hardware in the minor phase.
ele cropa o vídeo de 1h50 e 1h50.
Uhum. Tipo Twitch, eu acho. Tipo Twitch.tv. Acho que o Twitch faz isso também. So again, we finished the coding, but initially we had some problems with the batteries, so that's why the drone didn't run before. So we are now building. The battery was a Chinese one, like this one, and it didn't have enough current to power our motors. So we are now trying to put two of these in parallel just to check if they can work. If not, we have just another thing we can try that is using a dual cell but only using one of them at a time. And that's it. I don't check it here. Can use it after. Você fez algo tipo 100 mil FPS pra carregar ali, né?
200.
Por que se ela 138?
Arredondei pra cima.
Oh shit.
Não, muito pequenininho. Eu podia começa a pegar fogo. Precisa fazer a parte de controle. Podia usar o App Inventory. Jamais.
Não, mas aí tem que acessar um web, né? Fazer o socket. O que tá feito agora tá rodando no processing no meu computador.
Já tá ok?
Ué, não sei porque a gente não consegue ver o que o Arduino recebe. Mas o ESP recebe. Se o ESP recebe, ele deve mandar pro Arduino, entendeu? My dad did some borrachinhas, as I even like to call it.
Onde estaria isso? Projetos.
Não tem não, eu acho.
Micro-hexa.
Eu não botei não. Precisa daquele Explorer.
Explorer. Barulho. Caraca, várias pessoas.
All this time I pictured you standing next to me, so we could go find things we've never seen.
No.
I remember us, I was young in the sun, I knew how the end was. Now the story's changed, and the was fading away, wants to stay until the daybreak. I was young, 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 I was young. I remember you with your ruby skirt, when you made me hold you. Now the story's changed, and the was fading away, won't you stay until the daybreak? And I love, 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 and I love.
Okay guys, so let's test it out. Not sure that it will work, but
ever since I was little looked like fun. And it's no coincidence I come. And I can die when I'm done. Maybe I'm crazy. Or maybe you're crazy. Or maybe we're crazy.
vai funcionar.
Não vai funcionar, cara.
Tá, liga.
Pô, aí continua saindo, animal. Que bosta, assim. Continua saindo.
Que bom, só pra sair daí assim.
Agora é FTDI. Oi? Agora é FTDI. Desligou.
É, mas agora...
Não dá, depois do Nietzsche não dá. Não, demorou.
É, era problema.
Tá dando raiva assim na boca de tipo assim, lá.
Cara, você tá puta pouco. Wrong, nice. Ah, no, todo está apagado.
Come on, be my guest. Baby, I will always be blind. Come, let's get obsessed. Fire starts from a spark, cause you are my seed. Been here so long in my life, like a second skin. You always familiar, you're always fun. You come from the spine, you're always round. Maybe you come and like you and I'll just be, and I'll just be, and I'll just be, and I'll just be, and I'll just
So, why do I have some trouble with the visualization of the avenue? What is the user?
Oh, alright.
follow the sun. Which way the wind blows, when this day is done. Breathe in the air, set your intention, dream and spin. Tomorrow's a new day for everyone. Brand new moon, brand new sun.
AM2 is on. Okay, it's working now. Era trash. Lixo na memória. Tá, segura ele aí.
Pegou 2 meses?
Tá tentando estabilizar assim.
Cherish this moment. Cherish this breath.
Give me a power.
É que eu não botei torta. Assim, torta.
Some idle?
Só tem proporcional. Arrumei de fixar isso aí. Fez a micro-hexa-drone inteiro.
O FCD não dá, o FCD é feito um negócio gigante, mano. Falou.
Aí eu respondo.
Você viu isso?
Tá funcionando, mas sei lá. Vamos testar. Não vai demonstrar que isso tá. Como que eu vou mandar o comando?
Dando.
Teoricamente, se a gente botar o SP, a gente consegue comunicar com ele. Não, não dá. Tem que ser pelo SPDI mesmo.
Eu consigo comunicar. Agora eu preciso programar isso aqui.
Pra usar tipo um serial, sabe? Vamos ver. Eu vou...
Bateria?
Não sei. Fucking setting.
O que você sabe?
Ah, ia escrever e reiniciou. O toque reinicia.
Meu vídeo não tá nem aqui. Meu Deus, eu vou bloqueio lá embaixo.
Ó. Até descobri. Dá uma olhada.
Dá, mas eu estou muito focado, velho.
Então deixa aqui.
Loop is good.
Deu pra tipo dopado de baixo. Reiniciou.
O problema é esses três motores que eu pensei que era muito rodar. Então eu mandar o save de vez. Preencher 6 de vez não pode pensar.
Tá, então vamos testar. Você quer que eu sete todo mundo?
Eu tenho opção.
Tá, sim. 82.
27.
Tá bom. Tá na caixa que voltou, cara.
Não tá,
É dentro lá da caixa de baixo. Tá estressado, não vai dormir.
Quando começa a procurar coisa e olhar duas vezes mesmo, eu fico bobo estressado.
Você tá estressado.
Estresse técnico. Eu não consigo achar uma fucking cola quente no fucking quarto de
Eu já
quatro,
vi cola
quatro
quente em algum lugar.
Eu tô lembro de uma ação usando aqui no chão.
Não tá na mesa lá não. O pessoal tava mexendo com cola quente. Né?
Aqui no chão. O vídeo voltou no vídeo, não tava lá não.
Bom, agora o bagulho pega. Iniciou. De novo. Iniciou.
Então não funciona.
Iniciou. Damn it fuck. Damn it fuck. Let's see. PWM is at a high frequency.
Agora vai bater
Bom. It's the fucking battery! Shitty battery! Damn it! Okay, guys, so here is a progress.
Mas ele iniciou no final.
Não, eu que desliguei. Vai, desligou. Damn it! Initialization failed.
Mas
Desliga.
assim pode ligar ele.
Initialization failed. This is bad. This is bad. This is really bad. We may have burned it. Repente, listen.
Foi como quantas vezes?
Sei lá, cara. Um bico de corrente, alguma coisa. Ei, pode queimar. A lua tem ação, tá regulada. Demos. Tem outra ideia? Cara, mas é a única coisa que eu posso fazer. Se tiver alguma outra ideia.
Muito, muito bom.
Então, foi isso, cara. Não sei se dá pra fazer. Não tá tão fácil.
Vai simples de tudo isso, não tem.
Cara, vamos tentar fazer tudo aqui. Sei lá, foi sobre corrente, pode procurar um W, procurar um top. O quê?
Por que você não passa por um regulador, cara?
Não importa, cara. Foi 6 amperes aqui. Aí é 1011. Tem mais coisa aqui. Ah, foi. Segurei ele. Vamos lá. Beleza. Os dois, né?
Beleza, né?
Isso é fucking ruído, velho. Eu vou aumentar a frequência do pedalzinho. Sessenta e dois kHz. A gente usa todos, né? Viram?
Não tá bipando rápido dessa vez.
Isso. Acho que a frequência altera também o tempo do milho. Então, milho é um contador também. Calma. Tô contando.
Não, também.
Isso aqui.
Muito doido. Ele vai ficando rápido. Você vai ver muito descrito.
Segura?
Tá só ligado.
Mas se já foi uma comunicação com ele. Entendeu? Meio do Excel, alguma coisa assim. Bom, vamos finalizar?
too much? Did you get enough? Does it set on fire all the things that you touch? And it fills me up, it starts to shine, and I see it burn when you bring me sunlight.
So this is the end of the transmission. We have been here for about
10 hours.
10 hours, so we couldn't make the drone fly because of the battery problem, and with the small one it is possible, but we are really tired now and we need some debugging on the hardware part because it seems that the MPU is resetting, so maybe we need some more capacitors and so on, but that takes time to debug. So I really appreciate for all you guys that watched us and stayed with us. If you like it, you can subscribe to the channel and subscribe to the live coding
Subscribe at
channel.
YouTube and at live coding. And if you want to find out more about the project, to be on GitHub, so I think we have the link on the live coding channel page. And yeah, it's pretty much it. We will open source the project in a few weeks when we get everything working right. So yeah, we'll get the first prototype running. So that's it. If you want to find a little bit more about PID and some things about that, you can visit like the YouTube channel if you're watching from YouTube. Yeah, you have it.
Stay tuned. We maybe do another live streaming to complete the work. We still have to code the Android app so that you can control from the smartphone. We have to do the serial communication part. So there are a few things, a few wires that needs to be soldered here and be finished. So thank you very much and see you around.